So good morning, everyone. Welcome to the Consequences workshop, or the second edition of the Consequences workshop here at the RecSys conference. I want to start by thanking the other organizers, which are Olivier, Jeunen, Thorsten, Joachims, and Yuta, Saito, who are here. Myself, Harrie, Oosterhuis, Flavian, Vasile, and Yixin, Wang, who unfortunately are not here today, but may join us online. We've set this workshop up together, and we're very proud of the program that we have here. What we're going to talk about today is recommender systems as decision-making processes with consequences. So the idea here is to look at recommendations as interventions that have results and can have significant consequences that are important to consider. So think about things like causality, counterfactuals, sequential decision-making. What difference does a recommendation make? What would be different if a different recommendation had been made? This year, we received even more submissions than last year. In total, we've accepted 15 papers. I've made a word cloud out of the titles. You can see here, it gives you some idea of the topics that we'll see today. Of course, recommender systems are the largest word here. We have also learning and evaluation is I think the second largest, and then you can see content casual, of policy, bias, ranking, offline. So that gives you some idea of what to expect for today. We have 7 paper talks in total. We also have poster sessions, and we have 3 very nice keynotes and a tutorial. All the papers that you see today, by the way, are available on our website. To give you some idea of the interest where our interest comes from, what I've done here is I've made a frequency graph or a bin count of author affiliations. I didn't normalize this, so I didn't remove. So if there's a lot of people on one paper, they're all counted double. If people are on multiple papers, they're counted double again. But you can see here we have a lot of interest from both industry and academia, which we really like because we think that synergy works very well. And a pretty diverse set as well, although Amazon clearly has a lot of people on their papers. Today is divided into 4 sessions. Each session starts with a keynote or a tutorial, and then we follow it up by 1 or 2 paper presentations. These are the keynotes. We're going to start today with Michael Jordan, who is calling us all the way from California. Then the second session is going to start with a keynote from Minmin Chen from Google. Then I'm going to give a tutorial after lunch. And finally, in the afternoon, we have Wang from the National University of Singapore, who will give the final keynote. And the total program looks like this. Again, you can think of it as a keynote followed by a paper session each time. Okay, that leads me to introducing the first keynote speaker, which is Michael Jordan. Michael Jordan is a Pei-Hong Cheng Distinguished Professor at the University of California in Berkeley. He works on, his research interests, I should say, bridges the computational, the statistical, the cognitive, and the biological and social scientists. He's won a lot of awards and has received a lot of recognition. I'll name some of those. So he received the World Laureates Association Prize in 2022, the Ulf Grenader Prize from the American Mathematical Society in 2021, the IEE John von Neumann Medal in 2020, the Ichkai Research Excellence Award in 2016, the David E. Rummelhart Prize in 2015, and the ACM AAAI Alan Newell Award in 2009, and the IMS Medallion Lecture in 2004. Again, this is a selection. So it's no surprise then that in 2016 he was named the most influential computer scientist worldwide in a 2016 article of Science. This was based on Semantic Scholars Program. So please join me in welcoming Michael Jordan.
All right, thank you. It's nice to be talking at a conference on recommendation systems. It's one of my favorite topics in all of machine learning for a couple of reasons. One, it's about decision making, and 2, it has a social element to it. And so those themes are going to definitely come out of my talk. So let me take a moment here to get my desktop shared. There we go. That looks good. And okay, good. All right. So please tell me if you have some problem with screen.
Good.
Okay, so on the title there, you'll see a few words that are seemingly related to the theme of the workshop. I'm going to argue they're more related than you might think. All of the themes that you have in your title have kind of an asymmetry. There's a directionality, causal, sequential, and that directionality, I think, is something we haven't focused enough on. And so we're going to focus on that here. There's going to be agents on both sides of a interaction, and there's going to be an asymmetry. One agent knows more than the other. So this is, in economics language, a principal agent kind of situation. And we're going to be interested in the interaction of economic concepts with the machine learning concepts. Okay, so that's the idea. So I can't help but say a little bit about the current dialogue on AI. I think many of us in this field are a little bit alarmed by the terminology. We've been doing machine learning for quite some time and felt it was making a lot of progress as an engineering discipline. And suddenly it came to be called AI again. And you know, AI, the 1950s perspective, is not really that helpful. It's a different perspective than the machine learning perspective. So it was roughly John McCarthy's idea is, you know, to mimic the intelligence of a single human being and build computers that, you know, improve on that and mimic it and improve on it. So it's a wonderful, interesting thing to think about. It's not really what's happened with computers. We don't have thought in computers. And we do have things that are more akin to information flow and augmentation of human intelligence and internets of things, and all sorts of interesting artifacts have emerged. And so anyway, AI is being used there, but it's a little bit of a problem to use the old terminology in this new context. In particular, if you're thinking about making a computer as smart as a human, and then sort of putting that out there, putting it into an existing social system or technological system, it's not really clear what the overall engineering goal is when you do that. Is it to have the overall system be good, better, faster somehow? You know, should the overall system be better, or is it the individual level it should be better? So it's just not really clear how to think about it this way. All right, so a counterpoint that is kind of the underlying theme of my talk is that if we want to think about intelligence, that's fine. It's a little bit of a vague term, less so learning perhaps. But anyway, intelligence is as much about a collective as it is about an individual. You know, ant farms or ants, collections of ants are smarter than each individual ant. They can build things and bring food, and then markets are kind of collections of humans that have their own properties and their own intelligence. A market can create and be robust and react and so on. And then moreover, I think even more importantly, if we see ourselves in the era of an emerging engineering field that involves humans and data and decisions and so on, if we're going to talk about goals for that field, instead of just building systems that are cool or making money with our computers, those goals should somehow be expressed at the level of the collective. And we're not seeming to me, at least, to do enough of that. And in fact, there may be new forms of collectives that will emerge. You know, examples like markets and ants, we've had that for a long, long time. But, you know, there's now work on new kinds of democracies, new kinds of decision-making processes, new kinds of commerce. And recommendation systems are kind of a leading edge of that way of thinking, that system somehow produces something different or better than any individual human, and it has its own intelligence. All right, so I'm not going to spend much more time on this, but I think that slide shouldn't have stayed there. It's the same slide. Okay, so if you go to the machine learning literature per se and ask, are you working on collectives, you'll sort of see a picture like this. The federated learning paradigm is argued to be an example of it. So federated learning, I think many of you know, there's a notion of a server that is building a global model, and then there are local edge devices who may or may not build local models, but they do have local data. And the overall goal of the system is to transmit the local data or to transmit some privatized version of that to the federated server, who builds a global model that somehow benefits everyone. At least that's one way of saying the goal. Or it could be just to benefit Google. So, you know, the research questions are often about Can you make this robust? Can you make it private? Can you make it converge quickly, and so on? But I think that's really missing the what's really happening in a real world problem where architecture like this makes sense. It's missing the economic side. It's missing the social welfare issues, the collective idea. Okay, so stepping back, it's important to think about the nodes in these kind of graphs as not just nodes that are sources of data, but there are people, and their data is often valued. In fact, data is not really a great term. It might be their creative works, the music, the songs they've been writing, the poems, the novel they've been writing. And we're all working on our phones all the time and on our computers. So, much of what we do in our creative life is sitting there. And somehow it shouldn't just be aggregated and streamed, and there should be a benefit cost model, and there should be a participation by these creators of value. There should be an explicit valuation, and there should be an explicit market mechanism to not just treat them fairly, but really to make a market so that something better happens than just building a centralized model. All right, so that kind of language, I hope you can sort of see there's microeconomics ideas there that are being blended with machine learning. And in microeconomics, the engineering side of the field is really mechanism design. And so we want to build learning aware mechanisms. And on the other side, we want to think about mechanism aware learning. So there has been some of this. None of this is overall perspective is that new, but it's just not that common. It's certainly in the machine learning discussions, and even in places like recommendation systems, there's often not a direct discussion of economic principles and ideas of what is the actual economic mechanism, and are people incentivized to be in this mechanism, and so on. When there is discussion of mechanisms together with learning, it's generally an auction theory. So there's learning of auctions and so on. And in this talk, I'm going to broaden the perspective to talk about other kinds of mechanisms that are not auctions. Just to give a better sense of why I think these are important problems. In the real world, I've been working with a company. I'm on the board of the company and scientific advisor. It's called United Masters. And it's a company for musicians, really. And it is the CEO is Steve Stout there, who's a friend of mine, and he's a legendary hip hop producer and entrepreneur in the music world. Everyone knows him. And this company is a three-way market. So think like a recommendation system, but like with a third axis to it. So there are musicians, and they make music. And they should be thought of as agents who are providing something that they value. It's not just bits to be streamed to a Spotify-like service. It's music to be streamed to the consumers, and the consumers value the music. And some of that value is created by direct connections. If one of the musicians on this in United Masters, of which there are now about 3 million, they will know who is streaming their music, and they will be able to make offers. For example, come play at a venue or come play at a wedding or something. But much of the value is created by the third part of it, that they're brands. So United Masters signed a contract with several entities, including the National Basketball Association. So if you go and listen to music, or if you watch a clip on the NBA website and you hear music behind it, that music is provided by United Masters, and it's literally a musician. And when I say musician, these are young people, typically 16 to 20-year-olds who are making music at home, and they're good at it. And it's the music that a lot of the young people are listening to these days. And so they are now in a market because their music is being listened to on the NBA website. And the NBA and other brands can then reach out to them and say, your music is appealing to a certain demographic, and you make more of it, and start to develop partnerships. So that's actually happening. It's been happening now this is about 5 years old. And it's growing quickly, 3 million. So where's the AI or machine learning behind this? Well, there's quite a lot. It's 3 million, and it's growing fast, and there has to be fairness, and there has to be an actual matching algorithms. There has got to be adaptive algorithms here. And so there's quite a bit of microeconomics and machine learning in this platform. All right. So So let's just, that's kind of the market, building side. You kind of hopes give you maybe a concrete example of an actual market that is bringing value, in fact, creating jobs. There are 3 million people who are signed on, and many of them actually make significant money out of the website. So it's an AI platform, if you will, that creates jobs. It's a gig economy kind of made real in the music world. But now let's return just to kind of more classical recommendation systems and just the decision-making aspect. In markets, you have to make decisions, but let's just focus only on the decisions. And so, here's kind of a little diagram of recommendation systems, but let's now think about them when there's competition. Okay, so, you recommend to people movies or books, and if your system gets large, many people will be using your system, and there might be a scarcity issue. Now, in classical recommendations, there was no scarcity. You were recommending things that were in the computer, and you could easily copy the bits. And so if you recommended the same movie to 100,000 people or 10 million people, and they all want to see that movie, no problem. You just copy the bits. Same thing with books. You could copy the books really quickly nowadays. So recommendations have grew up in an era where there was no real issue of scarcity. But as soon as you start recommending real world goods that you can't just copy, like restaurant seats, if you recommend the same restaurant to 10,000 people, just because your recommendation system does that, you create congestion. And then there's many other examples like this. You can't recommend the same street to every driver. You'll create congestion again. And this is not a minor issue. You could just say, well, I'm going to load balance. I'm going to cap the number of people I send to a restaurant. I'll never send more than 100 people to every restaurant. But now the question is, who do you send to the restaurant? And it makes no sense to take the first 100 or just arbitrarily, randomly do it. That's not how people want to behave in the real world. They want to be matched. You wouldn't do a college admissions thing where you just take the first 100 people who applied and they get to go to the college and no one else does. There's got to be some notion of utilities and values and matching going on as part of a recommendation system when there's scarcity. And so again, this is not entirely new, but it's just not that common to talk about it directly, that we really need mechanisms to do this. There's got to be utilities. There's got to be learning together with all of that. Okay, so the alternative, instead of creating just a classical recommendation system for something like restaurants or street segments, is you create two-way markets or perhaps multi-way markets. Both sides can have recommendation systems. The consumers can share information about their relationships to producers, and then vice versa. So you could have diners on one side and restaurants on the other, and both sides could have shared information. Drivers on one side, street segments on the other side. So this is different than a classical matching market in that all the preferences are learned. Classical matching markets like college admissions, you asked each of the players on one side, the applicants, to write down a list of their preferences for all the colleges. And that's just not possible in a world like restaurants or street segments. It makes no sense. So we have to put learning into the matching algorithms. Okay, so that's a little bit of background on why I've been interested now for nearly a decade in problems at the interface of machine learning and economics. I could go on a little bit about other kind of concepts in machine learning, like fairness, privacy. These really have economic side to them. You can't be just absolutely private or absolutely fair. It's relative to trade-offs. It's relative to the utilities of the players in the game. I may or may not want privacy depending on the overall goal of the system or my risk function or my loss and so on. So I think economics with machine learning is just kind of critically important for going forward. So anyway, these are some of the problem areas I've been working on myself, and there are many people I think working on these, not nearly as much as some of the other big topics in machine learning, but I think that's going to change. So the first bullet, so I'm going to spend some time on a couple of the bullets. I've decided to pick a couple of topics that I'll highlight here. Let me just say about the couple of bullets I'm not going to talk about. I'm not going to talk about the first one, but the first one's really important. We're really good in machine learning at finding optima. We can find optima in high dimensions, amazingly high dimensions with non-convexities and stochasticities and so on. And we have upper bounds and lower bounds and algorithms that achieve these things and all. It's really been amazing a lot of progress. But in the problems I'm interested in, there aren't really optima generally. There are equilibria. and the equilibria shift as conditions change, the environment changes. So you want to worry about dynamics in the context of finding equilibria. And now we're in kind of the world of fixed point dynamics and not optimum, not gradient descent. It won't work in domains like this. So anyway, there's a lot of work in my group and other groups on that kind of thing. So what I will talk about today is this thing about information asymmetries I already alluded to. And I'm going to talk about calibrating predictions. And so this has to do with when you're in a team and you're in a group. If there's not calibration, then you don't have a lingua franca. You really can't work with each other. So we're going to talk about kind of how systems can be made to be more collaborative. Okay, so let me start with the first part of the talk. So this is an area that I've been developing with my colleagues Stephen and Michael and Jake. They were all well, Stephen and Jake were with me at Berkeley. They've now moved on. Stephen's at MIT and Jake at Chicago, and Michael's at Stanford. So I'm going to tell you a little about what contract theory is if you don't know already. Contract theory is a part of economics. It has not been a statistical theory. There's not been learning involved and so on. It's kind of like auctions, classical auctions. There was just values and not learning. And we're going to augment contract theory with statistics and for some real world problems that I'm going to tell you about. Okay, so just one slide on what is contract theory. So I don't think I really said on this slide, but let me just step back even a little bit more. The mathematics of microeconomics, a lot of it is fixed points and equilibrium and so on, and part of it is game theory. When you start talking about the strategic side, then it's game theory. Game theory is kind of a forward formalism. You set up a game, or someone gives you a game, and then you predict what's going to happen if that's the game being played in the world. And the prediction often has the form of, say, Nash equilibria or Stackelberg equilibria. That's your prediction about a behavior in the world. So like in many disciplines, scientific disciplines, you're making a prediction about what you see in the world. And if your theory is a good one, you'll make good predictions. And, Nash equilibria are not such great predictions in lots of situations. Stackelberg are perhaps better, but there's huge literature on all kinds of blends of various kinds of equilibria. Now, if you're an engineering-minded person, you want to go the other direction. You want to say, I have a desired outcome to achieve in the world. Can I design a game such that if players play that game, that outcome will be realized? So that's the inverse of game theory. And really, you should think about the theory of incentives as just the inverse of game theory. And in game theory, you have different kinds of equilibria, say Nash, where there are symmetric relationships among the players. And the inverse of that really is auction theory. But you also have these asymmetric equilibria, things like Stackelberg equilibria, where there's a leader and then there's a follower. The leader, it's not that the two agents play simultaneously like in a Nash equilibrium. There's no symmetry. Rather, someone plays first and the other agent sees that action and then reacts to that, maybe best responds to that. So now you can ask, what's the inverse of Stackelberg equilibria? And that's what contract theory is. All right, so in contract theory, it's instead of calling it leader follower, you often use the language of principal and agent. And so the principal wishes to get some job done. They can't do it all by themselves, or they don't want to. There are agents out there who are going to do the job. They may know more, they may have local conditions, or they just may have more time on their hands. And so they're going to possess some private information that the principal doesn't know, because if the principal knew that, they might just do it themselves. So the principal wants to incentivize them without asking them to reveal their private information. And so why do they not want to reveal their private information? Well, competitive reasons, also just to be able to get a good deal in the payment they're going to get. So the overall goal of such a system could be very precise. It can be an overall social welfare. It can be a revenue. So that's like auctions, but it's different from auctions. And so the best historical example was the airlines in the 1980s. The airlines were failing, and they were using a model where every seat in the airplane had the same price, and it was hard to price these seats. So ideally, you would know people's willingness to pay. You would figure out who was willing to pay more and who was willing to pay less, and charge an individualized price. That's called price discrimination, and it's either not legal or not feasible. but it is a fact that some people have a real need to get from point A to point B, or they just have more, more money, and they have a higher willingness to pay, and so they might pay $1,000 for the flight. And so if the airline charges, 900, that's great. They get almost all of that income. There's very little surplus. But if they charge $900 for everybody, there'll only be a few seats filled, and they lost the opportunity to fill all the other seats. So they bring the price down, to $100. Now all the seats are filled, but they lost the opportunity to get that $1,000. So I think you all know what the answer was, and it was called contract theory. But you create different fares, different kinds of service. And the difference in service can be not all that big of a deal. Like a little bit of glass of red wine and first in the line is kind of enough to trigger the willingness to pay of some customers, and you charge them a lot more. And so now the game is not simply an action, but it's a menu of actions. And an action is a price service pair. So business class, and here's the price. Economy class, and here's the price. And you give that entire entire menu of options to all of the customers, all of the agents. So they all see it, but now the symmetry is broken because they have different willingness to pay. So they look at it and say, well, given my willingness to pay, I'm going to pick that option. And if you set up the menu correctly, people will self-select. Some of the people who have higher willingness to pay will pick the higher option. Others will pick the lower. The plane will be filled, and everybody will have gotten sort of what they want, and the airline will have gotten significant revenue. All right, so this was really critical historically. The airlines were able to then make money again, and people complain a lot about this system, but it really makes it possible to have airlines. We wouldn't have airplanes if schemes like this hadn't been invented. Okay, so anyway, long story short, we have this asymmetry of information, and here maybe it's clear why an agent doesn't want to reveal their private information. If I reveal my willingness to pay to the airline that I'm willing to pay $1,000, they'll charge me $1,000. And so I hide that, and the airline knows nothing about me and has to give me the same options that everybody else gets. Okay, so I have a negotiation advantage. Okay, so that's kind of classical contract theory. And as you can see there, there's not any data analysis. There's no machine learning there. It's just smart people sat in a boardroom at an airline or whatever and figured out services and prices and kind of adjusted those over time. All right, so now let's turn to to versions of contract theory that really critically are going to require learning. All right, so the problem we've been working on, we call it the FDA problem. The FDA, Federal Drug Administration, runs clinical trials. Clinical trials collect data and make decisions. And what do they collect data about? Well, about all the possible, about drug candidates. So they're doing hypothesis tests. Here's a drug candidate. Is it a good drug or not? Should it go to market? And if it goes to market, what are the conditions? What's the licensing terms and so on? This is a huge cost. Here's some numbers from particular therapeutic areas. Phase 1, phase 2, phase 3 in the United States costs tens of millions of dollars per therapeutic area every year. And you all know about this from the vaccines. It wasn't enough to get 100 or 3,000 people. You had to get 36,000 people, and that cost a lot of money to do it really, really well. So it's very important. Okay, so what kind of problem is this? Is this just a statistical data analysis problem? Have low false positive rates and low false negative rates? Well, it's partly that, but that's only half of the story. Because the principal is doing statistical hypothesis testing, or classification, if you will. They only have partial knowledge. They don't know whether these drug candidates are any good or not. So they run the clinical trial, and it's causal inference that they're doing. But the problem is, or the issue is, that the hypotheses they're testing are not just coming from an existing scientific theory or from nature, or they're just not are coming randomly. They're coming from self-interested agents. So who are these agents? Well, these are the pharmaceutical companies. They are the ones who have the technology to supply drug candidates to be tested. And they can supply as many as you want. They can supply tens of thousands of them. They just kind of tweak a protein and get a new candidate. Now, the principal doesn't want to test too many candidates. That costs a lot of money. So they like to incentivize the agent to only send in good drug candidates, but that's private information. And the agent probably doesn't want to reveal that. They probably have competitive reasons, and they also want to get a good deal. They want a good license, good terms, and so on. So they don't reveal their internal knowledge about a candidate. Now, moreover, the agent doesn't actually know a drug candidate is some just protein they've kind of adjusted, mutated, and they may have done a little internal testing, but it's not at all clear the drug will actually work in the real world. So you have this very information asymmetry situation. And I would argue this is very, very common in all kinds of situations involving networks, involving people. Information is distributed around and not just kind of randomly. It's not just about decentralized learning. It's about information asymmetry. There's reasons it's held in some places and not in other places. And that is very much critically important for understanding what the overall system is trying to do and how to manage that. Okay, so let's think about the statistical problem for a moment. So how should the FDA test? All right, well, they are just being a good statistician, so they do a Neyman Pearson test. So let's imagine there's just two classes of drugs, bad drugs and good drugs. Bad drug doesn't mean it's actually hurt you, because they definitely rule that out in various ways. But a bad drug means it just doesn't help you. Okay, so that's theta equals 0. A good drug means it helps you. All right, so it should go to market. And they set up all kinds of tests in their clinical trials. They gather enough data, they get power and all that. They do a good job. And they have numbers something like the following. They're a little more stringent than this, but if it's a bad drug, the probability of approval is something like 0.05. So that's a false positive rate. It's really something like 0.001. And there are different numbers during the different phases and so on. If it's a good drug, theta is equal to 1, the probability of approval might be 80%, so that's the power. And now you can ask, is this a good protocol? And the answer is, well, yeah, it's optimal. It's the Neyman Pearson test. All right, the problem is that there's no economics here and no incentive structure. And so it can and will be gained. So let's look at two cases. In the first case, a small profit is to be made. So suppose it costs 20 million to run the trial. And if you're approved, maybe you would make 200 million in a year, say. And so now you can do a calculation. You be like the CEO of the drug company and this FDA, both can do this calculation. It's a counterfactual calculation. It says if theta is equal to 0, which I don't know if it is or not, but let's imagine it is for a moment, then the expected profit, given all the numbers I have on the page there, is minus 10 million. All right, so the CEO looks at that number and they say, okay, engineers, bioinformaticists, only send in candidates that we're really convinced are good ones, because otherwise we're going to lose money. And of course, they know, again, a little bit about which candidates are likely to be good. They did some internal testing. They know something about the protein. They put their good engineers on the problem and so on. All right, so they're only sending sending good drugs to the candidates to the FDA. The FDA does a Neyman Pearson test, and the approvals are all good drugs. That would be a wonderful world if we lived in that world, but we live something more like in case 2. So there's a large profit to be made here, say 20 million. Sorry, not 20 million, 200 million, 2 billion. Oops. It costs you 20 million to run the trial, and you're 2 billion if you're approved. All right. And so now the counterfactual calculation is that if the drug were bad, the expected profit would be 80 million. The CEO will look at that and they'll say, send in as many drugs as you possibly can. Now, why are they doing that? Well, it's because of that 0.05. Because if they send a lot of candidates in, there's a good chance they'll have some false positives. Those will pass the process. They'll go on the market, and they won't hurt anybody, but they won't help anybody either. And there are lots of drugs, many, many drugs on the market like this. Eventually they get supplanted. People realize they're not helping and so on, but they make some money in the meantime, 2 billion. So this would be a drug like ibuprofen or something, or even not even that big. Okay, so you've got to, obviously, from this kind of thought experiment, you have to take into account the incentive structure here. Otherwise, you're going to make bad decisions. The overall system is not a good statistician if it's not thinking about incentives. Okay, so anyway, we have worked on this, and we have a new set of ideas that we call statistical contract theory. And I'm not going to give a lot of details here. I just want to give you a little flavor of it. We have now several papers on it. Basically, as in any version of contract theory, there's a contract, and a contract has a number of steps to it, and you could opt in or opt out. So the agent arrives and they look at this contract and they maybe walk away. That's fine. But if they opt in, they then pay a reservation price R, say 20 million. They then choose a payout function, what they're going to get depending on the state of nature, depending on the clinical trial. And they choose it from a menu that we design. So this is like business class and economy class. There's going to be some licensing agreements, and they're going to cost different amounts of money and pay out different amounts of money. Okay. All right. So that's kind of classical contract theory, reservation price and a menu of options. What's new is just the statistical trial. The clinical trial is run, and it yields a random variable that's done in a causal inference experiment. So Z is drawn from nature's true distribution, P of theta. No one knows theta, but nature knows it. And so you get data from P of theta. Having gotten Z now, the agent receives the payoff, F of Z, using the payoff function that they selected. They self-selected a particular function given their expectations about Z. The principal then pays that out, so their utility depends on F of Z, and it also depends on the truth theta, because over time the FDA will be understood to be doing a good job or a bad job, and so their utility will need to depend on theta. Okay, so with that set up, you now have a mathematical problem. You can analyze this set of contracts, and you can ask questions about what does it mean to be incentive compatible? If you're incentive compatible, how do you design an optimal menu? And what do these menus look like in particular problem domains? All right, so again, we've been working on that in several papers. I just want to kind of briefly introduce some of the highlight concepts here. Whenever you're doing this kind of microeconomics, the first thing you worry about is incentive alignment. You have to give conditions for incentive alignment, otherwise the game just is not played and the system doesn't work. And so you see in the gray there, the definition of incentive aligned in this setting. It's a contract that has an expectation under the null hypothesis. So that expectation is under Z drawn from P of theta naught. So that's a counterfactual. Theta naught is if the drug doesn't, it's a null agent, the drug doesn't work. Okay, so counterfactual, we say if the drug doesn't work, then the payout would be F of Z minus the reservation price. And that needs to be less than or equal to 0. Otherwise, you're just the FDA is just losing money. Okay, and they're not going to do that. Notice that just the classical Neyman Pearson P less than 0.05 protocol is not incentive aligned. Easy to see. Okay, so that's incentive alignment. All right. Now, are there incentive aligned contracts? What do they look like? And so we've proved a general theorem that's shown at the bottom of the page here that says that a contract is incentive aligned if and only if all payoff functions are E values. What's an E value? Well, E value is something akin to a P value. Instead of being a tail probability under the null hypothesis, it's an expectation under the null hypothesis. So it's a random variable X that's non-negative, such that under the null hypothesis, its expectation is less than or equal to 1. So it's kind of a measure of strength of evidence. If the evidence is less than or equal to 1 under the null, then it's kind of evidence against the alternative, or it's evidence that it's consistent with the null hypothesis being true. If it's bigger than 1, it's evidence against the null. And in general, that's now an emerging area called E values. And these non-negative random variables are in general non-negative super martingales. Okay, so anyway, that's the definition of E value. And what our theorem states is that a contract is incentive aligned if and only if all payoff functions are E values. So one direction is easy, the other direction is less trivial. But it is a connection between an incentive theory, a contract theory, and a statistical or machine learning theory, if you will, about evidence. Okay, so we've been starting to roll this out in various domains. We've done this in federated learning, where we are incentivizing data sharing in federated learning. So again, you want to cooperate now to build a better statistical model that each agent could do individually, but you want to view it in an economic setting where the agents are incentivized to play the game and not free ride, not decide that they're not going to send any data if some other agent is sending the data. So this mechanism accounts for that. So there are a couple of papers right there that talk about this in a little bit more detail. And I will talk about the latter paper with Anantha Krishnan here on the next few slides. Okay, so this paper was just a week old, and I just want to kind of almost provide publicity for it. This is with Navasini, Anantha Krishnan, Stephen Bates again, and Nika Haktalab, colleagues at Berkeley. And so again, we're doing contract theory, and it's statistical, and we're trying to delegate data collection. So this is a little bit more not just incentivizing people to provide data, but incentivizing people to collect data. So we want to delegate that. A principal wants to delegate that. Okay, so there's, this again, there's real world problems here. There are services that will, you can delegate your data collection to them, and they try to make a economic model out of this. And we need to think about how would you design contracts for these data collection services, and contracts in the kind of mathematical sense that I referred to. Okay. All right, so the contracts are going to, just like before, measure some notion of risk or accuracy or whatever, and they're going to pay the provider as a function of the accuracy they get. So we're going to bring in the statistics again in the design of the menu. All right, and so the challenges are just real contract theory challenges. We don't know some things. There's some asymmetries. And so, and just to give a little bit more flavor of the language when using contract theory, there are two kind of classical notions of hidden information. One of them is called a hidden action. It's known as moral hazard historically in the literature, that the agent could do some action and may do the action after they see the menu. And we don't know that they're doing that or not. We'd like to incentivize them to do it if it's useful. And that in this setting, we have the problem is we have only a noisy estimate of the learned model's accuracy that an agent is providing, and we'd like to incentivize them to make that better. And we don't know if they're doing that or not. That's a hidden action. Hidden state is called adverse selection in the contract theory literature, and that has to do with ex ante, or before you've actually seen the contract, seen the options. It's just a fact about you, your state. So that would be the achievable accuracy that you don't have any control over. If I knew that, I could design, I could do better. I could know which agents to incentivize to, to provide data, but I don't know that. Okay. So anyway, in this paper, we go through contract theory approach to this, and I just want to mention a couple of the results. So first of all, if we look at the utility that's achievable in what's called the first best scenario in contract theory, that means where there's no hidden actions or hidden states. So the principal gets to see everything. They're omniscient. So we can get a constant factor multiplicative approximation to that utility just in the space of linear contracts. So linear contracts do respect our criteria on the previous slides, and they are e-values, and they're a simplified form of e-value. And in this particular setting, they give you a good approximation factor. We also can get an additive approximation with a contract that's a little more complicated, but it's still a convex optimization problem. Okay. All right. So if you're interested, those results are on the archive, and I encourage you to have a look. All right. So let me just check my time. Can I ask the organizer how much time I have left?
Yes, you have about 5 to 8 minutes, depending how much. So in total time, 15 minutes. So it depends how much.
Total time is 15 minutes. Okay, perfect. 5 to 8 is actually 8 should be just right. So this last part is with, again, colleagues at Berkeley, Anastasio, Stephen, Clara, and Tiana. This is a topic we call prediction-powered inference. And it fits into this talk because this is kind of about collaborative learning. We've got one system that has built a learning system and is doing a very good job, and we'd like to use it for our particular purpose. And we've got to worry about how that interface is achieved, how biases that are inherent in the principles model, if you will, can be mitigated at the level of the agent. All right, so the general setting we're looking at here is where somebody has built a model, perhaps AlphaFold has been built, that makes really good predictions in some domain, and we'd like to use that model to do inferences in a different domain, or use it to do inferences of a kind that weren't anticipated in the original data collection and model building exercise. And so protein structure is a great example of this. There's hundreds of millions of now amino acid sequences whose protein structure has been predicted by AlphaFold. It's known that the accuracy is quite high, and everybody is quite impressed, as they should be. But you know, there still is some doubt about, can you do science with these predictions? Are they as good as data? And what does data mean here? Well, there are hundreds of thousands of actual crystallized protein structures that are known, and it's a big difference: hundreds of thousands versus hundreds of millions. All right, so here is an example of a hypothesis test that was done in biology, a pretty important paper back in 2004. People were interested in the importance of intrinsic disorder in proteins. So intrinsic disorder, most proteins like to fold in a big clump, but occasionally there's some strands that kind of hang off. And it turns out now, years later, we know those strands are actually quite important. You can lay strands on top of each other and form little grills, and put those in membranes and control flow through membranes, and many other ways that are used. So intrinsic disorder, which reflects quantum effects, means they're strands. And this paper was looking at, do those strands matter for the use of proteins? And they measure that by phosphorylation of the protein. All right, so it's a simple statistical setting. We have at the bottom left there, you see odds ratio. We're calculating the probability of intrinsic disorder given phosphorylation divided by the probability of intrinsic disorder given no phosphorylation. That's called an odds ratio. If that is 1, that's the null hypothesis. There's no difference. If it's bigger than 1, we would reject the null. So it's just a gather some data, calculate an odds ratio. Is it significantly bigger than 1? All right, so long story short, I'll go back to that slide. When they did this in 2004, there was only 10,000 structures in the protein data bank, and they did their odds ratio and got confidence intervals for it, and those confidence intervals covered 1. So there was no, they couldn't make a conclusion, okay? Come forward 2022, these authors said, let's redo that same experiment, but now let's use all the AlphaFold data instead. In fact, it so dominates the crystal structures that they just only use the AlphaFold data. And they calculated the same odds ratio, and they made a confidence interval in the odds ratio, and they said, oh yes, there's an association. All right, so that sounds great, but it's, leaves you a little bit worried. I'm not really using real data here, and I'm making a scientific conclusion. Is that reasonable? And in fact, you might worry because this is being done all over the place. Here's some examples just from recent papers in Nature Science and PLOS and so on, and in a wide variety of domains where people are using predictions from machine learning systems and using those to make decisions, again, in this sort of decentralized setting. Now, here's the problem, which is that AlphaFold is really good, but it makes errors still, obviously. Here's an example of an AlphaFold prediction on the left. The actual experimental structure is on the right. And you can see, in fact, there's intrinsic disorder, and it's important. We didn't know that a priori, that it was making this kind of error. But when we start to form this odds ratio, these kind of errors can accumulate. All right. And now this slide is the most important one in this part of the talk. So let me just take a second to be clear on it. The x-axis here is the odds ratio. If that were 1, we have no association. We did a big Monte Carlo version of this where we took out half the data and we got the true odds ratio for the held out data, and that's that dotted line there. And then we did the AlphaFold predictions, and we made the confidence interval based on them, and we got the gold confidence interval, which is very nice and thin because it's based on a huge amount of data, but it doesn't cover the truth at all. Okay, so in both cases, you're not the actual odds ratio is not 1, so you do reject the null hypothesis. That's good, but you did it kind of in a dubious way. Now, so if you just say forget that, let's just go with the data we got, the 100,000 crystal structures. You get the gray confidence region, which does cover the truth. That's good, as it's supposed to, but it also covers 1, which means you can't make a decision anymore. Okay, so neither is very satisfying, and so this new approach called prediction-powered inference gives you confidence intervals. It's the green region. They are true confidence intervals in that they cover the truth provably with the asserted probability, but they tend to be much smaller than the ones that ignore the predictions. So these are, the green region is using AlphaFold, but it's correcting it in a way to make it into an actual confidence interval, whereas AlphaFold is highly biased. This looks a little bit like semi-supervised learning in that there's labeled data with predictions and unlabeled data where you have predictions but no actual labels, but it's different from semi-supervised learning. There you're trying to improve the predictor via your unlabeled data. Here, we're not trying to improve the predictor at all. We take AlphaFold as given. We're trying to take its confidence interval and adjust it to be a real confidence interval based on the labeled data. And let me just show you a couple of other examples. This is a protein expression. You put a protein in a gene and ask whether it's actually expressed. And you can see on the lower right there, the same kind of issue happens. The machine learning based confidence interval is very small, but very far off. And the green one is nice and narrow and covers the truth. And here's another example. This is the California census. You're trying to assess a logistic regression coefficient of income. We're predicting something about health insurance. And the machine learning model gives you a very narrow confidence interval, but it's really far. It's completely inaccurate. So you're sure of yourself and you're completely wrong. You can see the green one is better. It still covers the truth, but it's not that much better than the gray one. And that's because it's based on a bad machine learning model, but at least it's still being honest. Okay, so last slide, and then I'll finish. This gives you the story of how this is actually done. And let me just briefly say it. This is on the archive. But here, the picture is really it's not that complicated. On the left over there, you have a theta star. That's the true parameter that you'd like to estimate, like an odds ratio. It's out there in the population. We don't know it, but the supreme being knows it. Also, there is theta tilde f. That's the AlphaFold prediction. It's out there in the population too. And there is a difference between them, delta f. In this case, I used the mean as my parameter, just as an example. And so the difference delta is just a classical bias. In general, we call that thing a rectifier. And it will adjust the predicted population result to the actual parameter. Now, we don't know the rectifier. If we had it, we would just always adjust. But we can estimate the rectifier because it's just a population parameter. Just like any other statistical parameter, we can estimate it, and we do. So we put a confidence interval on the rectifier. That's the key idea. We don't just estimate the rectifier and then as a point estimate and then correct. That would be bias correction. We put a confidence interval on the rectifier, and in the middle diagram there, you take all of the plausible rectifications and you apply that to the AlphaFold output, and you get a confidence interval on all the possible corrections. And that is the green confidence interval on the right. So maybe the last slide, I'm not going to go into the details here, but this works it through in the case of gradient-based estimators. It does a little bit of addition and subtraction, identifies the rectifier, and forms a confidence interval in a particular way down in that theorem. And at the bottom of the page, you see that this does cover the truth. This confidence interval covers the truth with asserted probability. Okay, I think I'm done. I think that I just had one kind of more pictorial slide I just want to leave with you with, and I'll quit. I hope you see in this talk that there really are three foundational disciplines that somehow our overall field is referring to and is mixing and blending in various ways. Machine learning has always been a blend of statistics and computer science. To me, it really is just statistics, but done in a computer science style, if you will, and a deepening. But it hadn't had any economics in it, or not very much. And statistics meets economics, that's econometrics. It's about measuring the economy. It's not so much about design and algorithms, so not much computer science there. And then economics meets computer science, that's algorithmic game theory. It's all about algorithms and incentives and all, but very little statistics and data analysis and learning. And so in this talk, what I've tried to do is bring all three together in the same projects. And I also, in the real world, when I work in consulting companies and all, I often see that to solve a real world problem, you need all three of these elements together. So I'm finished, and I'd be happy to take any questions if there's time.
Thank you, Michael. Thank you for that very interesting and also very relevant talk, including very recent work. So it's really a treat. I want to open the floor to questions from both the offline and online audience. So for the online audience, you can use the chat or the Q&A function. And then are there already questions in the room? Yes, we have one here in the front. So Michael, could you let me know if you cannot hear the question?
I can hear you just fine, so hopefully it'll work.
Hello, can you hear the question, Michael?
Yes.
Hi, also from Amazon and Amazon Music, actually. So I'm wondering if the problem of the FDA probabilistic contract issue can be applied to how to allocate resources in A/B testing. You have offline experiments that give you some level of expected performance of an experiment. You have resources that you have to spend running the experiment online. And to some extent, it's also about how much you can do with the amount of resources and the amount of time. And there's competing teams, right? Because you have a set of things that you need to get done in the year. And I'm just thinking about it because as we do A/B testing, and specifically at Amazon, we are switching over from just a main, like more toward a Bayesian approach, but then we don't have yet a formal way of measuring the expected utility of those experiments given the evidence that we have offline.
Yeah, no, that's a great example. It is a contract theory problem, and clearly it's a hypothesis testing or statistical contract theory problem. There's lots of others that are Amazon, but not just Amazon. Many companies have these problems. You have third-party merchants or third-party sellers, and you want them to come onto your platform, and you're going to provide services to them, and you need to price those services. But you can only price it if you knew internal information, like their demand curve, how popular their product is going to be. But you don't know that. They know that, and you don't. And so, if the service is, do a A/B test locally, and you've given your resources or your data or your knowledge or your prior, you might be wanting other people to do something because they have a better prior than you have. So these are all situations where, yeah, agents have more knowledge and more ability, and then you want to harness that in a way that they'll buy into, and to make a working model out of that. And so, yeah, these are definitely all contract theory problems. And I think that being formal about it and putting it in those terms is really going to be important going forward. And literally, you will get out literal contracts like you get out. And let me also add, I'm not opposed to auctions as the more the symmetric kind of style. But auctions are a little bit heavy. Everyone's got to kind of write down a bid, and sometimes there's a little process. And it's a little hard to know how to do an auction. Contract theory is a little easier. You kind of see here's an option, and if I like business class, I'm going to pay for it and not. And it's you don't have to play the game with everybody else. It's this leader follower situation. So yeah, that's a great example. A/B testing is absolutely a good example of this.
Right. Again, for the online audience, if you want to ask a question, you can do that either in the chat, or you can, if you indicate you want to ask a question, you can turn on your camera after indicating it in the chat. We have time for another question. Is there one here in the audience? Okay, then let me ask a rather open questions to end on. So, Michael, you have the RecSys community here. Do you have a sort of a message or let's say an inspiration for us on a direction that we think we should consider in the future, or should look at more from your side? Yeah.
Well, I mean, I think I tried to do that in the talk, and then maybe just kind of re-summarize a little bit. But I think that a lot of recommendation systems are often best construed as markets, frankly. And so, it's really not just a platform that people go to and get a service and like a peer-to-peer linkage or something. There really are two sides to the market. There's kind of a provider and a producer and a consumer, and there might even be multiple other kind of players that come in. And so thinking about it that way, to me, gives you a better business model in some sense. So our little music, well, not little, it's a real company, but the music example could be thought of as a recommendation, you know, like Spotify. You could just say, okay, I'm going to recommend, you know, musicians to people based on what they listen to. Sure, you could have done that. But instead you say, no, it's a market building exercise. We're trying to, you know, find ways to find a valuation for the actual music and get money to flow. So, you know, to me, that's important, that whenever data is flowing, you know, be it a transaction in a classical recommendation system, or be it a, you know, a peer-to-peer, you know, data often has an economic value. And so I want to think about mechanisms that reveal that value and incentivize that value to be revealed in a true way, and do that in an adaptive way over time, and then do that in a social way. So, you know, a lot of the machine learning is really not social. It's that I bandit algorithms. I have a set of options, and I run some experiments, A/B tests, and I try to figure out which arm is best. And maybe I do a Thompson sampling, so it's a little more Bayesian. I have a prior on the arms and all that. You know, well, a very natural version, social version of that is to say, well, it's more like a recommendation system. My prior is gotten from everybody else, and so I'm going to start picking certain arms before other arms because everybody else has already shown those are good arms. And the overall system is a social system, and it's using recommendations to converge to bandit solutions. All right. Now, I think that's an interesting model that augments just classical recommendation systems. But then you run into the problem of scarcity. If everybody's doing this, you can't have everybody have the same action, you know, outcome. That's not going to necessarily work. So now it's got to be somehow utilities and all that brought to bear. So I just hope that, you know, people will start to think bigger about the business model. I think in machine learning, we used to assume our job was to provide, you know, predictions and information flow and large language models, whatever, and then someone would make money off of advertising, and everybody would be happy. And it's just not working. And so why don't we think about use recommended systems, but in a better, you know, market-oriented context, and create new kinds of entities? And then more on a technical level, this information asymmetry idea, I really harped on that a little bit. Let me just say that again. That really, in some ways, to me, is the effective issue, even more so than causal and sequential. It's rather that there was somebody that went first, and then someone that, based on what they did, went second. But it was all done in the context of awareness of somebody knows more than me, and I'm trying to understand how to work with that. So anyway, it's still kind of vague, but I just, you know, to me, these problems are going to take a while to work out. But I think that as a recommendation system community, if we don't start to face these, it's we're going to be kind of reduced to you know, something not as important as it should be.
Absolutely, yeah. That actually resonates a lot with the motivation for this workshop. So, well, thank you again, Michael. It's very inspiring and very informative.
All right,
you've almost filled up the room entirely in the meanwhile. So,
all right. Okay,
thanks.
My pleasure to give the talk. Thank you, everybody.
Once more.
All right.
Thank you, and well, have a good night.
Okay, goodbye.
Goodbye. All right, so we'll now move on to the first paper presentation, which starts with the paper Content Prompting, Modeling Content Provider Dynamics to Improve User Welfare in Recommender Systems, which I think will be presented by Siddharth Prasad. I can see that you're here.
Hi. Yeah, can you hear me?
Yeah, we can hear you great. Could you share your screen? And
yes.
Just as a reminder, you have 10 minutes for your presentation, and then we have allocated 3 minutes for Q&A afterwards.
Sounds good.
Yeah.
Okay, can you see my screen?
Looks great. Yes, the floor is yours.
Awesome. Hi, everyone. My name is Siddharth Prasad, and I'm a PhD student at Carnegie Mellon. Our paper is titled Content Prompting, Modeling Content Provider Dynamics to Improve User Welfare in Recommender Ecosystems. And this is joint work with Martin Ladnov and Craig Boutelier at Google Research. Content providers in recommender systems have significant impact on the overall user welfare of the system. And they're dynamic entities who respond to system feedback. a nascent body of work has begun to examine the incentives and behaviors of providers in recommender ecosystems. So for example, this recent work of Mladenov et al., they studied the design of non-myopic matching policies when providers might exit the system if they find that they're receiving insufficient user engagement. But providers are a lot more sophisticated than this. There are a number of complex provider behaviors as a response to the environment, but providers lack the ecosystem level knowledge to base their decisions on. So as I mentioned, providers can have a variety of complex behavioral responses to potential low user engagement. But the critical challenge here is that providers have little insight into the cause of this low engagement, and thus they are unable to make fully informed decisions. By contrast, the recommender has a comprehensive view of the landscape via, for example, sophisticated user demand models. And it is exactly this information asymmetry that causes economic friction and leads to suboptimal utility in the recommender ecosystem. So in these sort of cartoon illustrations here, you can, this pink provider is kind of facing a variety of different potential problems in the ecosystem, but doesn't have the view of the entire landscape to determine the cause of that issue. So in this work, we'll focus on the particular provider behavior of changing the content they produce, which we will visualize as kind of movement through content space, which is just this abstract embedding space. And this movement could be due to the provider's own changing beliefs, or it could be due to prompts, which are kind of actionable interventions by the recommender system that mitigate the information asymmetry that I just mentioned. So in this picture, if the provider could be incentivized to make the displayed move, the users who are displayed by these circles would be better served. If we think of affinity as being inversely proportional to the distances from the circular users to the provider who is displayed by the square. Now, if providers could simply be picked up and placed wherever the recommender wanted them to be in the content space, then this problem would just be akin to some sort of facility location problem. But of course, the reality is much different. Providers have their own beliefs and incentives that drive their own independent decision-making. So I'll now get into our first main contribution, which is an abstract model of provider dynamics and content prompts. Just to quickly put a basic setup, we assume the existence of some abstract embedding space, X, that contains a set of user queries Q and a set of content items C. There's some finite set of content providers K who choose to produce content items in C. When a user Q arrives, the recommender recommends the content of some provider K per a stochastic matching policy pi that just prescribes the probability that query Q is matched to K. Now onto the main provider model. So each provider has a true skill or innate ability to produce any given content item. This true skill is something that a provider must sort of self-discover. For example, by producing a particular content item sufficiently many times. And until this kind of discovery happens, the provider is guided by their skill belief for each content item. The provider also has an audience belief, which sort of bundles together the provider's belief of the landscape of user queries and the RS matching policy, which is obviously something the provider doesn't know. And finally, the provider has some degree of trust in the recommender. We assume that providers are myopic utility maximizers and at any stage produce the content item that maximizes their believed utility. And upon producing any content item, the provider experiences some utility and updates beliefs accordingly. Now, if provider dynamics are left to evolve on their own, we show that the recommender can actually end up in an arbitrarily suboptimal state. So to combat this, a content prompt is a suggestion provided by the recommender to break the information asymmetry that I've described and to enable the provider to make a more informed content decision, based on a more informed picture of potential supply, potential audiences, and their own skills. So we adopt the following simple form of a content prompt. The recommender reveals to a particular provider K some potential audience for content C, which tentatively is going to influence the provider's audience belief and potentially influence in the subsequent stage the content that is produced by the provider. So the recommender's job here is to implement a joint matching and prompting policy to steer the system into a healthy equilibrium. Note that the matching and prompting here are intimately tied together. The promised audience in a prompt needs to be delivered on by altering the matching in the subsequent stage appropriately. So I'll start by describing our analysis of the simple single provider prompting policy. So here, this is a super simplified setting where we assume all other aspects of the environment are fixed, including the matching and the decisions of all other content providers. We're simply zooming in on a single content provider and are going to think about how the recommender can issue prompts to steer that provider into a healthy state. So first, we give a policy for moving a single provider to a utility maximizing equilibrium state. And this policy converges in polynomially many rounds with high probability. And this is assuming that belief updates take a simple pointwise update. When belief updates kind of generalize across content items, so this just means that when a provider produces a particular content item, their beliefs are updated, and their beliefs about other content items can also be updated based on, for example, the affinity and the embedding space. So when this happens, provider prompts need to be sequenced in order to move a provider along a content path to reach a target item. So while incentivizability constraints make finding the shortest such content path NP hard, we give a polynomial time greedy approximation algorithm here. Now we'll talk about the joint multi-provider planning problem. This following simple example illustrates the need for joint multi-provider path planning. So here we imagine a situation where the system would be better off if these two display providers swapped locations. But applying a single provider policy in sequence here would incur significant welfare loss since this swap can't be executed at once. So we develop a mixed integer programming formulation to solve the joint multi-provider path planning problem. At a high level, the MIP involves decision variables representing the provider's content location at each time step. The main recommender decisions are the matching policy, the prompting policy, and the audience commitments. And the main MIP constraints simply enforce the provider dynamics. And the objective is to maximize time averaged user utility over the stages. So I'll now flash a small subset of our empirical results. Here's an illustration of a problem instances of one of our of an example problem instance. So here the blue crosses represent user queries, the red crosses are content items, and providers are represented by the green dots, and the skills. So provider's skill of producing any content item is inversely proportional to the distance to the green dot, but providers actually act based on the sort of confused point, which represents their skill belief. So this is the orange dot that is connected to a green dot. So here we plot the total user utility per each time step, the optimal prompting policy, the optimal policy without prompts, and the optimal stationary policy. As we can see in the larger instance, the non-prompting policy has a tougher time reaching the prompting policy, and the improvement over the myopic stationary policy, which is not allowed to change the matching dynamically, is significant. This table displays the improvement due to prompting, first at the final stage, that's the first column here, and the time averaged improvement due to prompting. And finally, here we have a user utility histogram that plots the number of users at each utility level. And this also shows a clear improvement due to prompting. So briefly, some future directions. The first important future direction here is to generalize our model, which makes a lot of assumptions on provider dynamics and the recommender knowledge. And the second is to scale our methods to the size of modern day content marketplaces. And that's all I have. Thank you.
Thank you, Siddharth. I'll open the floor for questions. Let me check the Q&A here. Okay.
Hi, this is Minmin from Google. I have a question. So in your optimization, have you accounted for, I guess, how hard it is for a content provider to shift their expertise in terms of producing new type of content?
Yeah, so I guess, we have not, that the difficulty or cost of changing content is not something we've explicitly considered in this model, but somewhat implicitly that is taken into account in the whole true skill versus skill belief. So maybe the content provider has some innate ability to produce some type of content that they themselves are not aware of. But in our model, the recommender has complete knowledge of these parameters and can kind of prompt the provider saying, hey, maybe try moving to this location content space. So I guess to answer your question, yeah, there are no explicit movement costs, but if the skill beliefs are such that and such a prompt cannot incentivize a move, then that would be taken into account in the optimization. So the optimization does take into account these skill beliefs, and any such prompt by the recommender needs to somehow overcome, a potential underestimate of the provider's own skills or their view of the audience. So that does need to be overcome in the optimization in order for the prompt to be successful. So hopefully that somewhat answered the question.
Okay, thank you for that answer. For the sake of time, we have to move on to the next speaker. Siddharth, thank you again for your presentation.
Great, thank you.
Ben London to turn on his camera. So Ben London from Amazon is going to present self-normalized off-policy estimators for ranking.
Hi.
Hi, we can hear you, but
You can hear me. Great.
Yeah, that's good. Yeah.
Can you see my screen?
Yeah, we see your screen. The floor is yours. You're good to go. Yes.
Fantastic. Thank you very much, Harrie. Okay, so yeah, my name is Ben London. I'm coming to you live from Seattle, Washington. I unfortunately couldn't be there in person, but fortunately, several of my co-authors are Giuseppe, Malte, and Thorsten. So you can talk to them after about the content. So we all know that recommendation comes in many forms, but the form that's most applicable to the work I'm presenting today is visual recommendation, where we have a large set of items that we could show to a user, such as a music catalog, and we want to select some subset and put them in the best order in terms of relevance to the user. A formalism that you're going to see a lot of today at the workshop is framing recommenders as contextual bandit problems. And the reason that I think that this is actually a very appropriate abstraction is that the feedback that we get on recommendations is incomplete in the sense that we only ever observe outcomes for the items that we actually show to people, but we don't know about what the things that we could have shown but didn't. And this is the so-called bandit feedback. So in a contextual bandit problem, there's some context, and in this case, it's given by the user, going to the system, maybe the time of day, and any metadata that we have about that. There's a set of items that we could recommend, and in the parlance of bandits, these would be actions. And then there's a policy, which is representing the recommender system, and its job is to reorder the items and then select some subset, usually with the top K rule. And this is what we call ranking, right? So these are ranking problems. Now, given the ranking, the user provides some feedback, and we're going to assume that we're in the semi-bandit setting where we can get feedback on each of the items that we show. So, recommender systems generate tons of data, and so I'm going to assume that we've collected a data set of contexts, actions, in this case, the rankings, and the corresponding rewards. But I will also assume that we have access to the policy that generated the data, or lacking that we've just logged properties of the policy, such as the distribution that it induces given a context. Or it could be the probability that we assign any item to any position in the ranking. Excuse me. And what we want to do is estimate the expected reward of a new policy, which I'm going to call the target policy, using the log data set. Now, if the target policy is the same as the logging policy, then of course our job is really easy. We can just average the rewards that we've observed, and this gives us an unbiased estimate of the expected reward. But in the case that the target policy is not the same as the logging policy, this is an off-policy estimation problem. And the difficulty here is that the distributions of the target and logging policy are different. So the standard approach to correcting the distribution from the logging policy to the target policy is importance weighting, or sometimes it's called importance sampling. And we use this estimator, which basically takes a weighted average of the rewards, where the weights come from this ratio of the target policy's probability in the numerator and the logging policy's probability in the denominator. And here I'm using the probability of an entire ranking for the time being. And just pictorially, what this does is, given some sampled actions, it just reweights the actions according to these importance weights. So actions that were very likely under the target policy but not so likely under the logging policy have greater importance. Now, the good news is that with certain assumptions, this can be an unbiased estimate of expected reward. But the bad news, as probably everyone here knows, is that this has very high variance, and especially when these probabilities here are the probabilities of rankings, because the probability of any given ranking can be very small under the logging policy. So one common way to address the variance specifically for ranking policies is to make some assumption about the way that users interact with rankings, and these are so-called click models. So one popular model is the item position model, which very simply just assumes that clicks are a function of a position and the item put at that position, but don't depend on any other items or positions. And this yields an estimator that it has, well, in theory, it could be unbiased, but in practice, we find that it has low bias, but it still has high variance. So lower variance than the naive estimator that I showed in the previous slide, but still not acceptable variance. Another very popular click model is the position-based model, which takes the item position model one step further and assumes that click probabilities factorize in a certain way. And this yields an estimator that in practice has lower variance than the IPM estimator, but unfortunately higher bias. And the reason for the bias is usually because we have incorrectly estimated what we call the position bias. So this is the probability that a user examines a certain position in the ranking. And usually we do a mediocre job of estimating position bias, and so that introduces bias into our estimates. So aside from the specifically the ranking setting in the standard bandit setting where we only recommend one thing, there are some common variance reduction methods we could also use, such as clipped IPS or truncated IPS, which is it reduces variance but is unfortunately heavily biased, and it has this requirement that we tune this threshold parameter M. Another method is doubly robust estimation, and this reduces variance, and also in the setting that we're considering where we have either the logging policy or the true propensities, this estimator is unbiased. But unfortunately, it has this practical requirement of training a reward predictor, which it's just an additional step that we'd preferably like to avoid. It's also worth mentioning that these techniques are compatible with the techniques, the click models from the previous slide. And I think that Harrie is going to present his doubly robust estimator for the position bias model later on today. But the point I'm trying to make with the previous two slides is that all of these estimators so far make some trade-off in accuracy in terms of their bias and variance versus their practicality, which is like the ease of use or the simplicity. But one technique which I haven't yet mentioned is what I consider to be an optimal trade-off of accuracy and practicality, and that is self-normalization. So the self-normalized IPS estimator, or SNPs estimator, is essentially just the standard IPS estimator divided by a control variate, which is generally speaking just a statistic with a known expectation. And in this case, the control variate is the average of the importance weights, and you can show that that has expectation of 1. And by the way, for this slide, I'm just focusing on the standard bandit setting. Now, self-normalization reduces the variance, and it has the nice property that it's asymptotically unbiased. But really, for me, what's great about SNPs is that it's parameter free. Like, you don't have to tune anything, you don't have to estimate anything, so it's really easy to use. Now, as I said, this is the estimator for the standard bandit case, but to our knowledge, no one has really applied self-normalization to ranking problems. And that's essentially what we did in this paper. So on the left is the SNPs estimator for a standard bandit problem, and on the right is our SNPs estimator, or a self-normalized estimator for ranking problems, where we've basically adapted the item position model. And the reason for this is that the item position model is essentially, or it can be written as a sum of regular IPS estimators with one for each position in the ranking, and so it lends itself nicely to all of the variance reduction techniques that I showed a couple slides ago. So in the self-normalized IPM estimator, or SNPM estimator, we have a local control variate for every position in the ranking. This is simply the average of importance weights for that position, and you can show that each of these local control variates also has expectation 1. Now, if we take this idea one step further, we can average the local control variates and get a global control variate, and just divide the usual IPM estimator by this global control variate. That's what I'm showing over here on the right. And we get another estimator, which we call the SNPM-G estimator for global. And the motivation for this, well, the intuition is that it has lower bias than the regular SNPM estimator, but also just a little bit less variance reduction. Now, speaking of bias, it's well known that SNPs has, or rather, it's asymptotically unbiased. And in work by Agapio et al., they actually bound the bias for a finite sample of data, and they showed that it's order 1/n. We extend and actually kind of refine or fix their proof technique to show that the bias of SNPM and SNPM-G is order k/n, and you can refer to the paper for the details of that. We ran some experiments on the synthetic data, and I'll just give you the brief takeaways. Our self-normalized estimators have the lowest mean squared error of any of the realistic estimators. I'm ignoring a skyline, which is unrealistic. And also, they, as expected, reduce the variance of the IPM estimator, which is what they are intended to do. So just some quick takeaways. I'm wrapping up on this slide, Harrie. The self-normalized estimators are accurate and parameter free, and for this reason, we think that they could be the default evaluators for ranking policies. Between SNPM and SNPM-G, this is an open question that we hope to address later. We also got some questions from reviewers as to whether we could apply self-normalization to the position-based model. And the answer is it's not easy because it's not straightforward that we would actually get a control variate by averaging the importance weights of the PBM. And just finally, we're very interested in how this compares to doubly robust methods. And actually, we can combine self-normalization with doubly robust, which is something that we'd like to try. So thanks again. Sorry for going a little bit over. Again, three of my colleagues are in the room with you, Giuseppe, Malte, and Thorsten, who I wasn't sure whether he'd be in the room, so I didn't put him on this slide. Thanks again.
Thank you, Ben. We have a question there in the center.
Hi, thanks for the talk. One of the questions, or one of the issues that I've had trying to implement any of these variations of IPS estimators is a lot of times you don't actually know or don't have a good closed form solution for what your true propensities are. Because it can be very, like the actual ranking process can be very complicated and have a bunch of eligibility rules and stuff like that. How do you have any like practical advice for how you deal with that? Do you make some model for estimating propensity? Like, I don't know if you've dealt with that in your situation, but it's an issue that we have.
Oh yeah, we deal with it all the time. I mean, like, assuming that we have the propensities is nice for for research and for analysis, but in practice we often don't have the true propensities. You can estimate them with Monte Carlo approximation by just either sampling from something or using samples that you already have. You can also try and learn the logging policy. Treat it like a classification problem where you're trying to predict the actions that the logging policy actually took. But unfortunately, if you are estimating the logging policy, then you're introducing some bias, and you could also be dealing with unknown confounders, which is an interesting topic that Olivier will be presenting later on today. So please tune in for his talk. But yeah, it's a hard problem, but we all have to deal with it.
All right, I'll use my power as chair to ask the final question. I was wondering then, is there, for me intuitively, or to think about these normalization factors, not the global one, but the one that differ per rank. How should I think about, like, what's the intuitive way to think about why one of these factors is larger or lower? Like,
why one of these?
What would that mean? Like, if I normalize by a larger factor for the first rank and the second rank, so sort of what does that imply for evaluation?
Yeah, I mean, if you're asking what it means if one of the control variates for a certain position is larger than another, I mean, it essentially means that that there could be greater variance in the importance weights for that position. And actually, I would expect there to be probably less variance in the higher positions in the ranking, because we tend to have policies that are very confident in what they put in the top, but the order at the bottom can get kind of can jump around a lot. So yeah, but basically it means that there's greater variance in different positions. Yeah,
I see. So it's yeah, okay, that relation makes a lot of sense. Okay, let's thank Ben and Siddharth, both presenters, for this paper session. Thanks again.
Thanks.
Then what I would like to do is first of all tell you to come back after the coffee break. That's at 11:15. We have a great keynote by Minmin Chen. I'll give you a small sneak peek of Minmin Chen's profile. I think we're really happy to have her as a speaker. I think it's going to be very inspiring. So I hope you're back with us in 45 minutes. We had planned now a coffee break and a poster session, but there seems to be something wrong with the poster session setup. So we were figuring out what's happening here. Either way, 11:15, be back for a great keynote and another paper session. Thanks, everyone.
All right. So it's a great pleasure to be welcoming Minmin Chen for our second keynote talk today. Let me give a bit of an introduction to Minmin. Minmin got her PhD in 2012 at Washington University, working with Kilian Weinberger on questions of domain adaptation, which is when I first actually saw her work. And I also know from Kilian, who speaks very highly of her frequently up to these days. She then went to Amazon and worked at Criteo for a while, but since 2017, she is at Google, now a senior staff researcher there. What really impresses me about Minmin's research is how she is doing deep kind of methodological design and research, and how she manages to get these systems into actually practically relevant systems at Google. Just to mention a few of those works that that also influenced my own work quite a bit. That she was one of the first to bring kind of off-policy learning into recommender systems with the YouTube recommendation system. And I've also closely followed her work on multi-stage policy optimization. So it's a great pleasure to welcome her today, and I'm really looking forward to it.
Thank you. Thanks, Thorsten, and thanks the organizers for having me here today and giving me the full hour. Actually, I think I've been talking about pieces and bits from this work at the different venues, but hopefully with the full hour, I will be able to give you a more holistic view of this whole program, which was built by, as you can see here, a lot of awesome collaborators from Google, who has really kind of enabled these lines of work and get it off the ground. And as I was sharing with Harrie and Thorsten, I think we as researchers were super lucky that many of the leaderships of the platforms that we work with was actually super supportive of this line of work, as you're going to see that some of these do hurt the short-term user engagement, but I mean these researchers and engineers of these production platforms was willing to actually sacrifice the short-term engagement for the long-term goods of the system, as well as long-term user experience, which was really, I guess, the ground for doing this line of work. So here's the agenda for today. I'm going to start with trying to establish the values of exploration and how exploration helps us in terms of data corpus as well as the content providers of the platform. And then I'm going to talk about the different treatments we have deployed in real production systems to help exploration, especially focusing on building dedicated exploration stacks to really help the flash and tail content on the platforms. And on the third part, I'm going to focus talking about two algorithmic directions that we have invested in. First is on neural bandits, and the second is to bring real-time learning capabilities to many of these recommendation systems. And I will end with discussions and future work. And feel free to interrupt me if you have questions during the talk. So first, to establish the values of exploration. So actually, when we first started the work about 2 to 3 years ago, we actually spent a whole lot of effort and thinking going through how can we establish the values of explorations, or how can we actually prove or show to the stakeholders of these different platforms that exploration is important, and we should really move away from this kind of pure exploitation-based systems towards having more exploration in recommender systems. So everyone here probably are knows that there exists a strong feedback loop in recommender systems, which leads to very exploitative behaviors, which create this gets richer effect, and then it also tries to tie users to familiar content, which really impacts or hurts user experience in the long run. And such strong feedback loop was because these recommendation platforms because they trained on historical user interaction data, so they tend to reinforce the kind of choices the user made. And and at the same time, since user can only make choices on the recommendations that are already made by these systems, so such feedback loop causes these kind of exploitative behavior, which is actually detrimental in the long run. So we believe exploration is the key to break such strong feedback loop. And then for exploration, there are two types of works that we think are in the space of exploration. So the first is we call it item exploration, where the goal is to surface relevant tail and fresh content on users' known interest. And the second is what we call user exploration, where the goal is to, for example, identify unknown user interest or to introduce users to new interest. And in this talk, we're going to actually focus exclusively on item exploration, but we do also have work in the other space. So if you're interested, please reach out and I can point you to the right content. So the challenge in starting this line of work on exploration is that when we deploy exploration treatments to these systems, we often measure neutral and negative engagement metrics. So the reason is that naive exploration treatment in a regular user diverted experiments often measures negative user engagement metrics because the type of experiment we run in terms of a regular user A/B test can only measure the cost of exploration in serving less certain content rather than showing to the user what we know about what they for sure will be interested. So the main research question we're trying to address is basically how can we establish the values of exploration. So as I was preparing this talk, I would actually look up the workshop page, and then the Confo contribution essentially wrote the thesis for us. So I mean, we see that the recommendation actions have consequences on two aspects of the recommendation systems. First is, as we highlighted here, it basically impacts or influences the kind of data we collected, which as in turn also impacts the kind of model will be trained after that. And then the second is also, as Michael Jordan mentioned this morning, there are multiple stakeholders on the recommendation platforms. So besides the users, the content provider are also an active participant of the platform. And then the recommendation actions actually have a very strong consequences for the content providers in terms of how they will strive or on the platform. So we believe the values of exploration can show in three dimensions. First is on data, second on the content corpus, and the third is on the content provider. So the challenge is that the intermediary benefits of exploration on these entities actually cannot be measured in a regular A/B test due to leakage. So what we mean by leakage is that because when we compare two treatments, one with exploration and one without exploration, because the two treatments, they will be sharing the same kind of data corpus and content provider on the platform. So if there is any impact on one treatment on any of these entities, they will be leaked through the other group. So as a result, we cannot measure the benefits. So in the end, what this is saying is basically in order for us to measure the benefits of these of exploration treatment on these three entities, we basically need new experiment design. So first, for us to measure the benefits of exploration on data collection, and then further to improve model training, what we did is basically essentially set up this data diverted experiments where there are actually two sets of experiments that are running concurrently. So there is the first set of experiments, which is running for the data collection. So in the control group, we run experiments which a treatment which has only an exploitation-based system. And then in the treatment, we were running a treatment where the ranking system actually has exploitation treatment added to it. And then we, in the second set of experiments, we're actually training two separate models, one model A on control traffic, which is purely exploitation-based, and then a model B, which is on the treatment traffic, which has exploration. And then we compare the performance of these two models to measure basically the impact of exploration on data collection and then on model quality. So here's the result we're seeing. Compare these two experiments. First, we see that exploration help in terms of reducing model uncertainty. So as the shown in the figure here, the control arm is showing in orange and the treatment arm is showing in red. And by comparing these two, we can see that exploration reduces uncertainty in the model we trained. And then in the second figure here, what we're showing is that when we compare the two models, the control arm, which is trained on the control traffic with exploitation only, and the treatment arm trained on data collected from the first treatment arm in the first experiment, it actually produces a model that has much higher quality, so that we see the gap between the user satisfaction matrix of the treatment arm is actually growing over time. And then in the second dimension, so what we're basically trying to show is that exploration can help improve the corpus reachability. So by corpus reachability, we're basically looking at two metrics. The first metric is what we call daily unique impressed corpus at K, which basically is a coverage matrix that measures how many content on the platform that are getting more than K impressions. So this is, you can imagine a purely exploitation-based system will have much lower numbers when you compare to exploration-based system. And then the second matrix we'll look at is we call discoverable corpus at X, which basically counts the number of content received more than X positive post-exploration interactions. So we designed this matrix to get rid of basically the confounding fact that in the exploration treatment, basically we're giving more impressions to these tail and flash corpus. So it could be that, well, these contents, they are getting more they're getting more interactions just by giving them more impressions. So in this metric, we actually we will stop the exploration treatment at certain time points, and then we basically measure after that how successful the content is once they are supposed to be survive on their own. So here, basically, we run experiments on these platforms for months. And what we can see here is on the left, we count the number of content which receive more than 100 post-exploration interactions in 7 days. And you can, what we can see here is that the treatment which has exploration treatment will have much more number of contents that are being discoverable compared to the control arm. And the figure on the right here is looking at the different cutoff threshold, which look at getting 1,000 positive interactions after exploration. And the same trend is observed. And another very interesting aspect we see is that the gap between the treatment and the control arm is actually growing over time. And when we're looking into why that's happening, what we're seeing is actually the content provider in the treatment arm, because of they are getting these exploration treatment, they actually create more content.
over time. So as a result, the gap between the control and treatment is actually growing. And so the comparison I just show you kind of compare, I guess, demonstrates the short-term effect of exploration in, I guess, when we're looking at how the corpus is performing 7 days after the exploration. So, but what we can imagine is that it will take time for content to actually to grow to, I guess, become a superstar on the platform, right? It will take time for a piece of content to receive less than 1 million clicks or views on the platform. So here, instead, what we're doing is that we look at the performance of these two groups in 3 to 4 months, and we look at the difference between control and treatment. The dotted line I'm showing you here is actually counting the number of contents that will be receiving 1 million views at that time point. And what we can see is, again, the treatment arm is getting much more content that goes to becoming, I guess, a superstar on the platform compared to the control. So in some sense, this is making the point that exploration is not purely helping these tail and fresh content just getting started. It is also help us actually identify some of these really high quality content which could have been successful, but without exploration treatment, they actually could not reach that stage. So this comparison is looking at the third dimension that we're talking about in terms of creation and then content provider. So on the left figure here, we'll look at on the platform, when we compare an arm which has exploration treatment versus an arm which does not have exploration treatment, how many more content providers are uploading new content between these two. And we can see a very significant difference when exploration treatment is on, then the content provider definitely has more incentive to create more. And then the right figure here is looking at content at provider retention. So we actually look at, so after 4 weeks, are these creators, are these content providers still creating and uploading new content? So again, we see a difference between the control, I mean, the on with versus the on without exploration treatment. But I mean, the gap is smaller compared to the left figure, which definitely speaks to the much more challenging problem in terms of content provider retention. So we need to do, I guess, more than just the initial exploration treatment. So actually, for many of us who work on this project, we have, I guess, this internal belief that, well, a system where the contents are much more uniformly, I guess, distributed among the corpus or content provider is a better system. But then at the same time, as researchers and engineers, we also have the desire to prove to others, well, such a system is indeed better for the user in the long run. So basically, we design these experiments with the hope that, well, if we can, I guess, if we can build a system where the corpus and the creator base is actually growing, then we want to show that that system is actually better than the current system we're in, where a small chunk of the content or providers are getting impressions or views on the platform. But the challenge is it's actually much harder to create that system. So instead, what we're doing is we did the reverse side, an ablation experiment, where we actually took out content and then creator from the platform. So in a sense, basically for each user, we black out some corpus and then content from the platform, and then we see how the user satisfaction will change in respect. So we did the ablation at the different percentage So 10% will be basically ablating 10% of the corpus, in some sense each user in that treatment group will only have access to 90% of the corpus on the platform. And then again, 20% ablation up until 50%. And what we can see here is definitely there is a huge impact in terms of user satisfaction when we ablate the corpus, which I guess prove the point that if the content and provider base is smaller, then the user satisfaction or happiness is going to be much worse. And then by, I guess, projecting that on the other side, that kind of help us establish the point that if we were in a world which the corpus and the creator base are much bigger, then it will be a much better stage to be in for the long run. And we actually run these experiments for months, and you can see that even at the end of that 2 month period, the long-term impact is still, you can still see that downward trend when the corpus is reduced. So once we establish the values of exploration, then the question basically comes in terms of how can we build, or like how can we shift these platforms from this purely exploitation-based system to a more exploration-based systems. So as we said before, so there are basically two high-level objectives we have. One is to basically to increase exploration coverage, meaning that we want as many content on the platforms to receive impressions and views. And then at the same time, we wanted to improve exploration efficiency, meaning that we want to still for these tail and fresh corpus still to show them to a relevant user rather than just showing them to some random user, because that will hurt the user engagement very significantly. So the hope is that when we were given that specific budgets that we can spend on exploration, we can basically spend it wisely so that we can actually increase the corpus coverage to the maximum extent. So there are basically two system treatments we were building. So first is basically based on the motivation that since the system is very much exploitation focused, so how can we actually build a dedicated exploration stack which can actually shelter these fresh and tail content to actually get started from competitions from the head and popular content because of the inherent bias in our existing platform. And of course, the second is how can we bring exploration-based treatment to these systems, like to the existing recommendation stacks, so that we can reduce this bias in the existing system and really accelerate the growth of the corpus. So in this talk, I'm actually going to be just focusing on how do we build this dedicated exploration stack for introducing or like for sheltering these fresh and tail content from the initial growth. So what we did is that we built this stack to have a few properties. First, it only serves fresh and tail items. So only items which are uploaded in the past X days or have less than Y positive user interactions are eligible to be recommended in this stack. And then second, it is relatively separated from the rest of the recommendation stack in the sense many of these new components we build, it's built for these specific corpus only. And it has the objective of improving exploration coverage and efficiency, relatively independent of the existing systems in the on the platform. And then the final recommendations from this stack will be served at floating position on the platform. So you can imagine the platform has many positions, And then for some specific positions, the final candidates will be pinned to their positions, while the rest of the positions is still fulfilled by the existing recommendation stack of the platform. And then similarly to the, I guess, the existing recommendation stack, it has multiple stages in order to be able to serve the content corpus, which are in orders of millions or billions. So one thing I guess that was interesting from this line of work was that we, I mean, especially for the nomination system, we actually build a multi-funnel system. As I mentioned before, exploration does have the trade-off between coverage and efficiency. A system that's really good at generalization ends up being not great in terms of bringing the most relevant content. So the idea is that we want to combine system which has high generalization capability, as well as system which has near real-time updates to reach maximum efficiency. So how can we combine them best together in order to balance between the coverage and efficiency trade-off? So the nominator for generalization we built is basically a two-tower DNN architecture, which has encoded the user and item features separately, and then a serving time is through I guess efficient maximum inner product search, find the most relevant and find the content for recommendation for this specific user. So in order for this system to optimize for coverage or for content generalization, one thing we did was to actually completely drop item IDs from this nominator, so that this nominator actually cannot rely on ID features for memorizing any historical preference of the items. And then we also exclude any features which are indicative of historical popularity of items. And then we also have another system which is updated in near real time. So the idea is that real-time systems should be able to react to the user feedback much more quickly, so that it can more efficiently identify which content are really relevant for a specific user. So what we did was basically try to minimize runtime of the different components in building this nominator, including logging, model training, model pushing, so that the end-to-end latency for this nominator is reduced from let's say 24 hours or days to just a couple of hours. And in order to facilitate that fast training and pushing, we try to make the system relatively simple. So it is basically a weighted self-attention model. So that once we have these two nominators, the question is, how do we combine them so that we have both the generalization capability of this two-tower systems for improved exploration coverage, as well as the real-time updates of this real-time nominator for exploration efficiency. So what we did was basically we separate the corpus which are eligible for this dedicated stack into two funnels. One is what we call low funnel content. So these are the content which are having very limited or even zero interactions on the platform. And then the middle funnel content, which are the content which has collected I guess a few initial interaction feedbacks in order to train this more memorization-based real-time systems. So instead of trying to achieve both generalization and real-time learning with a single nominator, so now we basically have these two nominators. One is specialized for generalization, and then one is specialized for real-time for efficiency. And then we use them to recommend content from these. The generalization is recommending content from the low funnel, while the real-time learning recommends content from the middle funnel. And by combining them together, then the system actually reach a much better balance between coverage and efficiency. So to measure the effectiveness of the system, we basically conducted a 1-month user corpus called diverted experiment, where in the control arm, we basically serve the main recommendation stack without any exploration treatment. And then in the treatment arm, we basically serve the system we just built, which has a dedicated slot that are reserved to show recommendation for these tail and fresh content. And then we compare these two arms in both the corpus matrix, as I explained before. That's the DOIC matrix, which basically counts the number of content on the platform that are receiving K impressions over time. So the K can go from 0 to 10K, as I'm showing here. And the second dimension that we're looking at is basically the short-term user engagement. So we can see here is that the treatment arm shows a very significant improvement in the corpus matrix, and we can see it's green across the different buckets that we look at. There's on this 1,000 K equal 1,000, we see basically around 12% improvement in the treatment arm. So it was very significant. While on the short-term user engagement, we do see a cost, but it was still relatively mild. So as a result, this was considered a good trade-off, and then it was able to be deployed in the system. Now, as I said, basically we have 2 lines of treatment. One is to build this dedicated exploration stack, and the other is basically to introduce exploration to the existing recommendation stacks. And now I'm going to basically move to the third part and talk about what are the different algorithmic investments that we made, which could be deployed in either of these systems in order to make exploration have either or both better coverage as well as efficiency. So there are basically 3 main directions that we were investing in. One is to basically build bandits and uncertainty algorithms. And then the second is to introduce real-time learning. And then the third was to improve on content generalization so that we can actually be much more efficient at the initial bootstrapping of these content. So there is actually a consistent theme between these directions, which is, since many of these recommendation systems nowadays, they are built on deep neural network-based systems. So we want to actually identify technologies which can really work well with DNN-powered recommendation models. So first, I'm going to talk about the neural bandits work that were actually built by, I don't know if she's here, but there's a poster session, I think, on Friday where she will be introducing more of these work. So if you're interested, please stop by. So recommendation can be very naturally framed as a bandit or connector bandit problem, where each user requests time t when a user coming in with a contextual feature ut, and then the system basically presented the user with an action, and then also observe the kind of feedback the user is provided, which follows an unknown underlying function f here. And the goal of the system is basically tries to learn this policy pi so that it can actually minimize its regrets or maximize the rewards it can accumulate over the long run. So many classic algorithms such as lean UCB or Thompson sampling with linear payoff has been extensively studied. But I think the main questions we are trying to address is how can we make these algorithms work with these DNN-based systems, which are now powering many of the existing industry recommender systems. So one of the, I guess here we have one industrial recommendation models, which are often used in the ranking stage of different platforms. So you can see here, it is actually a very large models that have like many deep shared layers in the bottom, and then some mixture of experts layers. And then there are usually multiple tasks which are trying to predict the different kind of reward signals the user can be given to the system. So in terms of building uncertainty-based or bandit-based approach for exploration, so as I said, there are the linear models like LinUCB or Thompson sampling, which is very efficient in terms of the uncertainty estimate, which is in closed form. But the challenge is that because of the representation power of these models are very limited, so it's actually, they are not great in terms of modeling the interactions between the user and item pairs on recommendation platforms. And then the alternative is this ensemble-based approach, where you basically build multiple versions of these deep neural network models and then try to get estimates in that way. But the problem is, well, it is in very high capacity, but the challenge is that it is very computationally expensive because, as I said, these models, they are huge by themselves. So you don't want to bring up multiple copy of that. So the solution we found was basically this neural linear bandits algorithm, which is kind of the combination of these two approaches. So it uses basically it is a linear contextual bandits on top of the representation powers of neural networks. So it uses the representation generated by these DNNs as the contextual features, and then estimate the uncertainty using a linear contextual bandit. So as a result, it's actually very cheap for uncertainty estimate, but also achieve good performance because of the representation power inherited from these DNNs. So here's a case study of how we integrated into the ranking model I just showed you before. So the first thing we did was actually we just picked a single task from this multitask ranking model. And then we added these pink components here, which are basically doing the uncertainty estimate for this specific head. And then using the contextual features from the model, using the feature, representation learned from this model as the contextual features, and then try to estimate the uncertainty. And then we use Thompson sampling to get the final prediction, which accounts for the prediction uncertainty, rather than just using the the prediction from the head itself as the final score. So I guess here is just a simple recap of Thompson sampling. So as shown here, we have 3 arms. So instead of just using the mean of the 3 arms, try to decide which action to pick. So in this case, we'll be picking action 2. Instead, we try to sample from this posterior distribution, which we estimated from the model, and then decide which action to take. So in this case, we'll actually pick the orange action because even though it has a slightly lower mean, it does have higher uncertainty, so that we end up exploring an arm which we are less certain about. So here, I guess we show the experiment results where we compare the control arm, which is the production ranking system that does not have any exploration mechanism in it, and then to a treatment arm, which adds the neural bandits exploration on the specific head we picked. One thing that was super interesting from this experiment is that we actually see both improvements in the corpus dimension as well as the user matrix. So in some sense, it does not really sacrifice the short-term user engagement for the corpus. And the reason we believe is that for these more sophisticated exploration treatment, which is really able to, I guess, not necessarily sacrifice the relevance of the recommendation for exploration, and especially on platforms where freshness or having tail recommendation is really beneficial to the user. So the user are actually looking for more fresh and tail recommendations. This kind of treatment end up being both beneficial to the corpus, in the sense that the discovered corpus was significantly increased, but at the same time, the user satisfaction or even just short-term user satisfaction was also very positive. So I guess one thing that people might be asking is, well, because you did this approximation where the uncertainty is only estimated after you get representation from the neural nets, are the uncertainty correctly estimated? So one thing we did was we actually compared the uncertainty estimate to the uncertainty which are generated by the ensemble model, and we show that these two are actually very positively correlated. And another test we did, which was more on the qualitative side, was basically to look at the estimated uncertainty and compare to some dimension which we know that should be, I guess, like for example, we look at the content age. So basically, how long ago was the content uploaded? We would expect that old content should have much lower uncertainty than a fresh content. And we can see basically there is a negative correlation between the content age and then the estimated uncertainty. So in some sense, I guess we're trying to show that the estimated uncertainty was making sense. And then, so after we've seen the promise in this direction, the second thing we did was to actually moving beyond this single task and going towards the multitask system, which is, so these ranking models, they are actually designed to handle the multiple rewards. So the question we're basically trying to address is how can we perform effective exploration for multitask ranking models? So the difference between the single task one and the multitask one was basically we need to identify features which works, or like representations which work for all these tasks that we are interested. And then another, I think, interesting thing we did was to also add in the contextual features, the features which are, we believe are relevant for the uncertainty estimate. So in terms of, well, I guess, how do we find contextual features which we can use for these multitask uncertainty estimates? So what we did was basically look at all the possible candidates in the learned model and see actually which one works best. So you can imagine, like for a model architecture like this, the shared bottom, because I guess these are the features all these heads are using, is to capture information that are needed for predicting all these heads. And then another is to look at the, I guess, try to concatenate all the different heads, or like the heads that are going to these tasks. And then another option is to look at the mixture of the combination of all the different experts that we use in the network. So what's interesting out of this comparison was that we found is the third option, which is concatenating all the representation from the different tower works the best, because as they are actually sit at the last layer that's connecting directly to the task, so the linear predictability assumption that's needed in these linear contextual bandits is actually most satisfied. And then the mixture of expert actually leads to some degenerated performance because there were actually a lot of highly correlated features in these experts. So then again, we conducted the A/B test experiment where we compare. Now the control is the one where it's doing neural bandits exploration with just a single head, and then the treatment is doing, I guess, the multitasked neural bandits. And then again, we see that there is improvement in the other tasks that we modeled, for example, in terms of predicting the value dwell time or non-value dwell time, they are significantly better than the control arm. And then I think another very interesting lines of work is to actually extend this to nomination stage, which has its own challenge because these nomination systems, it no longer uses these, I guess, a single tower DN. Now it has to have the user and the item representation factorized in order for efficient retrieval. So how can we incorporate uncertainty in this type of models is another challenge. For time's sake, I'm going to skip here and then talk about real-time learning. So I think the motivation for this lines of work is for many of these bandits or RL algorithms, they're actually designed to be an online learning paradigms in the first place. So the idea is that if we can get real-time user feedbacks on the items that we export, then we can actually effectively reduce overexploration or underexploration in the sense, I mean, if we find something that the user really like, then we can show them more. But then if the contents are really not getting feedback, then we can reduce. But the challenge is most of the existing recommendation stack actually uses offline training with end-to-end latency, which you can span across days. And so the work that we're doing is basically wanted to build a real-time ranking system, which has end-to-end latency that are in the orders of just a couple of hours compared to the most of the existing models, which are learned in the which has a latency around 2 days or even more. So the first attempt we did was basically let's just bring up these real-time models, which are trained every, I guess, 1 or 2 hours. One of the, I guess, encouraging thing we've seen is that, well, this system definitely has much more freshness and corpus matrix compared to the control, in the sense that having more real-time training can definitely recommend more fresh content. But then the challenge we're seeing is that these systems end up being recommending much less diverse content compared to the control arm, which we hypothesize is because of these continuous training actually causes catastrophic forgetting in these models, that it actually forgets the long-term dynamics that that happens in the past and overfits to the real-time data that we have. So I guess the main challenge in this line of work is that, well, compared to the nomination system that I told you about, which can have multiple nomination systems, one focus on generalization and then one focus on real time. In here, in ranking stage, there's usually just a single model. So how can we get a single model to do both generalization and real time is the challenge here. So the second approach we're proposing is basically this hybrid approach, which actually in some sense is very similar now to like these pre-train and fine-tuning approach that people have been doing in the LM or foundation model world. So that we'll have like these batch training, which has a much bigger high capacity model that are learned very infrequently and try to capture these long-term dynamics. But then we also have these real-time training phases where these models are fine-tuned on much smaller data chunks, and then they are learned much quicker in order to capture the real-time dynamics. I guess, yeah, this is basically the setup of the model. So we have the, I guess the gray out area are the batch models, which has much higher capacity. And then we are learning these, we call fast parameters, which are some fine-tuning components that has smaller capacity, but it also has much fast changing real-time vocabulary so that it can adapt to the real-time dynamics, but without changing without forgetting what has already learned in the batch phase. So again, this is we also did experiments comparing the control is the production system, which train in batch, and the treatment now is the hybrid approach, which combines batch train and real-time fine-tuning. Again, the great news is we see the improvement in terms of exploration efficiency, so that the user overall enjoyment was improved, and then the freshness corpus matrix is also improved. So now just, I guess, quickly in summary, so we've seen in the measurement side, so the benefits of exploration on users often take very long time to manifest. So as a lesson that we learned through this journey was that it's very important to, like at the beginning of your project, or try to basically establish or find what proxy metrics in order to compare successful exploration treatments. And then because our existing system is very much exploitation focused, so we really need this orchestrated effort, both in terms of building these dedicated exploration systems, which are purely focused on these fresh and tail content, as well as try to introduce exploration to existing stacks. And then in terms of algorithm deductions, there are many exciting opportunities to try to push both the frontiers of exploration coverage and efficiency. So in terms of future work on the measurement side, so there are actually, I think, some new breakthrough from the data science team in terms of building a new experiment framework that can actually measure the long-term benefits of exploration in one go. So what we have doing so far, it's always, we try to find these intermediary entities and show the value on exploration for them, and then try to connect those to the long-term user experience. So the goal here is basically try to design an experiment framework so that we can actually show the effect of exploration on long-term user in one go. And then on the algorithm side, I think for real-time learning, this is a direction we definitely wanted to continue invest. And then the content generalization part, which I wasn't able to talk about today. So the idea is that how can we leverage the better content understanding now we have in these foundation models and generalization capability to improve exploration for recommendation systems. And there's also an interesting, I think, the other direction. So how can you actually use exploration techniques to help for some of these also long tail problem in these foundation models. And then another direction that we're super excited about, I think Michael also talked about this morning. So recommendation system is definitely a marketplace, or it's an ecosystem with not only the users, but as well as the content providers. So as an active participant of the platform, their dynamics and incentive is actually much less understood on the platform compared to the user side. So how can we actually try to understand that, model that, as well as introduce that in building our recommendation policy is something that we're super excited about. Yeah.
Thank you very much for the exciting talk. Questions?
Hi, thanks for your talk. It's brilliant. I think it's about the exploitation and exploration dilemma, and you focus on the exploration models. But I think there are lots of choices to deal with this issue, like reinforcement learning or multi-armed bandits. What's your comprehension about these choices to deal with the long-term benefits for recommender systems and the exploration and exploitation dilemma? Thank you.
So I think as I talked about, actually a huge chunk of our work is essentially focusing on how to build like these bandits techniques into the recommendation models so that it actually is doing that active exploration. Yeah, and then of course the same will apply to RL algorithm with that additional, I guess, taking into account of the long-term dynamics of the user as they adapt it to the recommendation policies. So I think one thing we really wanted to emphasize here is, I mean, there is this active steps that you are doing in exploration, which is trying to acquire better data or trying to get these content and content providers to a level ground with the other players or content on the platform, which was not, I guess, more explicitly taken into account in the historical work even we have been doing in RL or on the platform. Yeah, which was, I guess, not like that exploration phase was not explicitly considered. That's why I think we're now doing this lines of work.
Other questions?
Thanks for a great presentation. The question I have is like the way you have introduced exploration in neural bandits is by adding uncertainty to some of the feature computation. So one way to do is also to kind of like add some noise to the final scores, which can come out of any models, right? And it can be like model agnostic. And it's easy to implement. So what are like, in your opinion, what are the disadvantages of doing that, of adding noise to the model scores and rather doing it in the model itself?
Yeah, I think that's a great question. So, I mean, adding noise is definitely one way to introduce like randomness or exploration to your system. But I think what we are showing here is that if you have a more efficient way to actually help you estimate where the uncertainty is, then it's much more efficient. So that's why what we saw is that treatment was actually helping user engagement. So I think like if we were to deploy a system which does random exploration or just randomly show recommendations to users, it will help with the exploration, it will help with the corpus matrix, but it will hurt the user engagement significantly. So with a more efficient system, what we can do is you can take that, I guess, budget or engagement that you can hurt, but you can spread that to much more corpus and content providers to maximize that benefit in the long run.
Maybe one final question.
Hi, thank you for your inspiring talk. I have a question about your hybrid approach. For this hybrid real-time training, and I'm wondering, do you observe any unstable issue when you try to cold start your model? For example, you are updating the slow parameter and the faster parameters into different stage.
So that's a great question. So in some sense, so this training is continuous over time. So at the very initial stage, we're doing the slow parameter update, which is just as your regular training of these models. And then we move that towards the training these fast parameters. So they're definitely design that we're doing in that fine-tuning component, for example, in terms of limiting the capacity of that, because we have much smaller chunk of data to train. And then there are a lot of, I guess, optimization in terms of what kind of optimization method we use, what kind of learning rate we use that really, I guess, stabilize. We didn't really observe a lot of stableness issues, but we did observe, I guess, the trade-off in terms of forgetting and adapting to that dynamic, which requires a lot of, I guess, very detailed engineering to figure out what's the right balance between the two.
I know there's a bunch of more questions here. I myself have a lot of questions too, but we're out of time. So my plan is to just phone a Minmin during lunch and ask all of my questions.
Yeah.
Right. Thank you again.
Sorry, maybe I probably with the class as well. So hopefully you enjoy or like I guess the work that we're doing is interesting to you. So if you're interested, we definitely have openings in the group as well as many of the platforms that we work with. So come talk to us. Thank you.
Switch, yeah. Do you want me to do the switch while you introduce? Okay. I think it's okay. So the next talk in the session is by Olivier Jeunen and Ben London. It's on offline recommender system evaluation under unobserved confounding, and Olivier is giving the talk. All set? You have the floor.
Great. Okay, great. Then I will get started. All right. So first of all, thanks to all of you for staying right before lunch to listen to my talk. My talk is going to be about how you can do sort of offline recommender system evaluation, which I think is a problem most of the folks in the room will have sort of encountered at some point. And this is work that I did with Ben London. So when I talk about recommendation, I like to frame things in like a certain way. So we will have a certain reward. This reward is going to be sort of influenced by a context and by a certain action. And then we have a logging policy that is going to, dependent on the context, going to decide what the actions are that it's going to take. And so maybe slightly less abstract, this means that we have certain user satisfaction that is being influenced by recommendations. These recommendations are being decided by a certain system we have in production, and that system uses features to decide what to show. And so one very sort of common question we might ask is, well, how satisfied are users with my recommendations, right? And so when you think about that question in this framework, that's very easy to measure, right? Because it's simply the sort of expectation of the reward, given that the actions are being sampled according to my system that I have in production. And because I have this in production, it's really very simply something I can measure from log data, right? So that's really just, we look at the logs and we just look at the sort of average satisfaction our users have. But now, the real question we really want to answer very often is, well, how satisfied would users be when I would have a different policy instead? So we no longer have this logging policy by knots, but I want to sort of intervene on the action distribution and deploy this policy by instead. But I don't really want to do that because that's very costly. I want to know the answer to this question beforehand. And so when you frame it in this way, it's clear that this is really an inherently sort of causal question. And so the real question that we're asking is whether we can actually sort of estimate this quantity purely from observational data alone. And so I think that people who do research into causal inference will tell you, well, yes, you can do this, but then you need to make a certain assumption. And that assumption is that there are no unobserved confounders. And this is a very crucial assumption, as I will show, but it's not something that's really talked about very often in the research literature. And so I will make this clear, hopefully, via the sort of guiding example. I'll make a few blanket statements here that might be wrong, but for the sake of this sort of thought experiment, I hope it will be clear. So let's assume that we all like pizza, right? Very simple statement. Some people really love to have pineapple on pizza, but then most people will really hate pineapple on pizza. So essentially, we have this one item which is of sort of general appeal, and then we have an item that's really, it's either hated or loved. And so we can really like sort of quantify these numbers, saying that, well, there's a certain probability that people will like to have pineapple on pizza. There's a certain probability that they will hate it. We will say that the latter is alpha and then the former is 1 minus alpha. And so we can sort of mold this setting into a table where we say, well, we have a certain feature now on the rows, which is saying whether you like pineapple on pizza or you do not like pineapple on pizza. And then whether I give you a pizza that has or does not have pineapple on it is going to affect your reward, right? So if I show, if I sort of give you a pizza that does not have pineapple, we will all be reasonably happy, but we'll be sort of 0.7 happy. But if I give pineapple to those who love it, they will be very happy. If I give it to those who hate it, they will not be happy whatsoever. And so like we can think about having a system like this. We have a certain system in production that is giving sort of pizza recommendations to people, and it's doing so in a reasonable way, right? So we have a system that is going to be sort of epsilon greedy, but also fully correct, right? So there's like a 1 minus epsilon sort of probability that we're actually always taking the optimal action for any given user, but there's a small probability that we're actually going to take the suboptimal action for sort of any given user. And so what that means is that, well, we can actually write down now for this sort of very simple thought example, what our data is going to look like, right? So we have certain combinations of context and certain actions, and they will lead to certain rewards. And there's a certain probability that all of these samples can occur in the data that we have. Now, of course, in many cases, you won't actually be able to very neatly write out what the joint probabilities of observing a certain sample. But again, for the sake of this argument, we do. And so when we think about doing offline evaluation in a setting like this, the question we might want to answer is, well, suppose I now want to have a policy that's just going to show a single type of pizza. It's either gonna have pineapple on it or not. What single type of pizza is actually going to lead to higher satisfaction? And so when you want to answer a question like that, you can do something like inverse propensity scoring. So you're going to do sort of off-policy estimation. What that means is very simply, you look at all of your log data, you sum over the log data, you simply look at, well, for the observed rewards, what is the likelihood that this action would be taken under my new policy, divided by the likelihood that this action was taken under my logging policy. And you can do this, and this gives you an unbiased estimator, and sort of all is well. Now, in the real world, very often we don't have this neat table where we've written all of these like sort of probabilities out. So very often you will have to somehow estimate this instead, because we don't really know the logging propensities. What happens is we look at all of the log data we have, we get a certain estimate for the logging propensities, and then when we're smart, we sort of try to validate these logging propensities in some way. So there are a few papers out there, not many, but there's a few that actually show certain sort of diagnostics that you can use to make sure that the logging propensities that you're using actually make sense to do sort of IPS. And so this happens really often, right? That we don't know these exact logging propensities. When you're working in sort of industry, this might happen because you have a very complex logging policy, and so you need to somehow get an estimate of the action probabilities you get at the end. But when we're in academia, this happens very often, because when I just get like a public data set somewhere, there's never essentially information in there about randomization, about the logging policy, about the system that was in production showing these sort of pizza recommendations to people. The problem is often even worse, because sometimes in these public data sets, we don't even have all of the features, right? And so we might not have this feature showing that people really love or don't love pineapple on their pizza. And this is a problem, right? Because it still looks like we can simply learn these logging propensities from data. We can still validate using these diagnostics whether these logging propensities make sense. The problem is that they don't, because this is a sort of unobserved confounder that we have now. And so we can still do IPS with these estimated propensities, but we will no longer have an unbiased estimator of the true reward you would get under your policy. And that's an issue, right? And so we can somehow simulate this sort of scenario and see what happens when we do it anyway, right? So suppose that we have this whole scenario. We have two different policies that we want to evaluate. One is going to always put pineapple on pizza. One is never going to do that, right? And then the question that I want to ask is, well, what would the expectation of rewards be given that I sample actions according to one policy or the other policy? And then there's two ways we're going to simulate somehow getting these estimates, right? One is going to be the sort of ideal way, where we know the true logging propensities, right? And so we know that this should work because there's no unobserved confounders. It's more of a check, actually, like a sanity check that this is going to work because we know it does. But then we can also do sort of estimated IPS, where we have these unobserved confounders, right? There's this feature that we don't know about, but we don't know that we don't know. So we'll just sort of get an estimate, like a best case estimate of these logging propensities anyway, and then see what happens. And so this plot shows what goes wrong there, right? So over the x-axis, you have this sort of epsilon parameter from the greedy logging policy. the different columns are showing different values of how likely you are to actually like pineapple on your pizza. And then the y-axis is showing the estimated difference between the reward you get from policy 1 and the reward you get from policy 2, right? And so sort of in the settings we have right now, the reward you get from sort of policy A1, so no pineapple on pizza, is actually superior. And so you can see for these two lines, like if a line is under 0, that means that estimator actually thinks it would be better to go with the first policy A0, right? And so that is not the true thing. And so the main sort of takeaway from this plot is really just that for most of the settings, there's actually a huge gap, right? There's a huge bias between what you get from the estimated IPS scores and what you should be getting. And that should be a problem, right? But now you might think, well, this might not be a huge problem because we have these diagnostics. You said we can sort of estimate these propensities, but we still have a way to validate these propensities. And you would be mistaken, because we actually prove in the paper that the existing diagnostics that we have, they are based on control variates, and we prove that they cannot uncover these types of situations. And this is not just for the very specific situation of sort of pineapple on pizza, but we really prove sort of mathematically that the problem of unobserved confounders cannot be uncovered by them. This is an issue, right? This should raise some alarm bells, I hope, because we're in a situation where we've seen that the existence of unobserved confounders can lead to really a sort of arbitrary bias in your estimates. It can completely switch the sign of your sort of treatment effect estimates. And we're also in a situation where we actually have no way of knowing that we are in this situation. And that's a problem, right? And so I think certainly when we're reading research papers, and the research papers make statements like, well, for simplicity, we're going to estimate the logging policy, but it's going to be easier if we assume that it's non-personalized, right? So we have certain features in the data, we could use them, but we just decide not to use them. Well, that's also now going to be an unobserved confounder. And so that is going to lead to biased estimates. And so statements like that might seem very innocent in research papers, but they actually aren't. So, right, that's essentially the main topic of my talk, highlighting this problem. We haven't really talked about solutions yet, but that's because they're also not that straightforward. But I think that, so talking about solutions is also important, right? So is there some way we can figure out when we are in this situation, when there are sort of unobserved confounders? Would we maybe be able to sort of prove that there's a bound on the bias that these confounders can incur? Maybe we can somehow make assumptions about, the strength of the unknown confounders based on known confounders, right? Like lines of reasoning like this are very often made in like the entire sort of research literature doing causal inference from observational data, because we're not the first ones dealing with these problems. But it does seem like, it's a problem that's flown under the radar for a while, because we just haven't seen many research papers talk about this. So then I will leave you with this. I hope this will spur some interesting lunch discussions. Yeah, and I hope you all have a great workshop and a great conference.
Questions about this?
Yeah. Maybe let me add one possible solution, which is also to think about how do we redesign, like how we build in business rules and the recommender systems that make it actually easier to report propensities, right? That would be another solution.
Maybe you're using that microphone. Yeah, this one's off. So,
any other questions? Harrie?
Hey, Olivier, this is Harrie. You mentioned at the end that we cannot know whether we're in this situation. But I wonder, is this still the case if you are able to do an intervention or some kind of online evaluation?
That's interesting, right? So I want to be careful of making blanket statements because I'm not really sort of causal inference researcher, but like certainly when you have observational data and experimental data, there's suddenly much more you can do, right? So suddenly now there's much more things you can actually estimate. And so that should definitely help your situation. But when you're not there, sorry, do you hear me, Harrie?
It's okay. Yeah. Everyone is very quiet so that we can hear you. Yes.
Ah, okay, sorry. Yeah, so I mean, yeah, maybe is the
okay.
Simple answer.
I guess the point of this was to point out a problem with all of the nodes. So I guess that fits. Thank you, Olivier, for the answer.
And with that, maybe let's wrap it up. This ends the morning session. We have lunch now, and we are back at 1400, right? 2 o'clock. All right. Thank you. Bye-bye.
So welcome back to the consequences workshop. So this is one of the afternoon sessions. So we have a tutorial by our organizer Harrie, followed by 2 paper presentations. So first we're gonna have the in-workshop tutorial by Harrie. He is of course, our organizer, and also he is the assistant professor at Lichtenberg University in the Netherlands. He's also a visiting scholar at Google right now. He has been quite a relevant and impactful research in the field of information retrieval, recommendations, enforcement learning, learning trunk, especially unbiased learning trunk, which is a topic of today, and also fairness in ranking. He has also won many best paper awards in recent conferences, including Wisdom and CIL. Today, he is going to be talking about Doubly robust estimation for position bias creeks, which is, of course, a very relevant topic in the workshop, including counterfactual estimation and unbiased learning trunk. This is actually what I did try to do, right? To extend Doubly robust estimation to somehow like unbiased learning trunk, but this is also something I wasn't able to do by myself, so I'm very much looking forward to how he do with this, Doubly robust estimation in ranking. So the tutorial is going to be roughly about 45 minutes, followed by 5 minutes Q&A session. So without further ado, Harrie, the floor is now yours.
Thank you very much for that introduction, Yuta. And thank you all here for finishing your lunch on time and being here. We'll see who didn't later, of course. As mentioned, I'm going to talk about Doubly robust estimation for position biased clicks. This tutorial is actually based on a choice paper that I published this year. And you might think, how can you build a whole tutorial on a choice paper? Well, the PDF of this is, I think, 35 pages long, so it's quite a big piece of work. The reason I chose this is because it covers sort of both the basics and the most recent involvements in sort of the core estimation for position bias. I'll show the slide at the end again, so you don't have to scan it right now. What I'm going to do is I'm going to divide this tutorial in 2 parts. I'm going to first start by talking about general counterfactual estimation. So I'm going to give a recap of some of the basic family of methods here. And the reason I'm doing that is because in the second part, I want to contrast how we do it differently in counterfactual learning to rank. What are sort of the difficulties that we see there, the problems we have to solve in the learn to rank setting that we don't have to solve in the general setting. Of course, I'm going to do my best to balance, to give sort of a nice introduction for those who are not that familiar with the topic, but also keep it interesting for those who are very familiar with it. So let's get started. So I'm going to start with a setting that has no ranking. So very simple single item recommendation. So the most basic setting, at each time step, we're going to recommend a single item to the user. And the goal here is to maximize the total number of user interactions. Whatever interaction it might be, if it's a click or a watch or a purchase, you name it. The setting here, however, is, you could say, off policy or counterfactual, in that we have interaction data logged using the production system policy, but not the policy that we want to evaluate. So this is a very standard setup. Today, you've, I think, seen this setup at least 4 times already. So it's this standard problem of, okay, I have data from one policy, how do I evaluate or optimize a different policy? And the very naive thing you might do is, if I have my policy here on the right with its propensities or its action probabilities, and I have some interaction data, is let's say that in my interaction data, someone interacted with item B, then I can look at my policy and say, okay, what is the probability of action B in this policy? And then the higher, the better. So the higher this probability, the better this is, because this was an item that was interacted with. Now, as you surely know at this point in the workshop, is that this is naive, because what I'm ignoring here by doing that is that there was actually a logging policy that decided that this would show up in our data. So there was a form of selection bias. There was a logging policy that decided to show B to a user, and that's why we saw that interaction, right? If it had made that choice, we wouldn't have seen that. So this logging policy will cause certain items to be over or under represented compared to the other items. So this is the basic form of selection bias that we have to deal with here. Now, just for some notation, right? So I want to estimate here the expected reward. That's what I would like to know. So R here is my reward function. Pi is is the policy, and X is some sort of context. So what we'll have here is we're going to sum over all the actions. On the left part, we have the probability of the item being recommended under our new policy. And on the right, we have the probability of an interaction with the item. This is basically how many interactions do I expect to get. Of course, I don't know this probability on the right. I don't know the interaction probability. That's what we aim to estimate. So the naive way would be just to replace that with the interaction we observed. And this is very much biased. And we can see that when we write out the expected value, because now we see we don't actually get the expected reward that we want to estimate. We get something else here, and we basically have this multiplication here with the probability of the item recommendation under the logging policy. So this is this over or under representation, right? So the more likely this item was to be logged by the policy, the more likely it's to be, the more weight it has in this expected value. But that's not what we want. We don't want the logging policy to have any effect here. So this is the basic problem here of selection bias. And now, again, this is a generic setting. How do we deal with this? The first method I want to talk about is inverse propensity scoring. Again, you've also seen this a couple of times today already. A quick overview, right? So the basic idea here is that I'm going to take the logging policy, and then I'm going to take the inverse of these probabilities. So if these probabilities, we can call them propensities. So a very low probability, like for item C here, becomes a very big inverse propensity. A very big propensity, like for item B here, gets a very low inverse propensity. So that if you were to multiply them, they would all get the same value, and you would not have sort of more weight for one item than the other. And then instead of directly matching this observation of the interaction B with my new policy, I'm first going to multiply by this inverse propensity. So by weighting the opposite way than my logging policy is logging, we're correcting for the selection bias in expectation. So this is the basic idea of inverse propensity scoring. In notation, this is also something that you've already seen today, right? Is what we end up with is this ratio, right? So we're still using the observed clicks. If I have, in this case, n observations, but I'm now going to reweigh it with this ratio between the propensity of my new policy divided by the propensity of my logging policy. So that basically means that if an item is underrepresented, I'm going to give it a large weight. So I'm going to pretend like it happened more frequently than I observed it. If it's vice versa, if it has a very large weight, then relatively it gets a lower inverse weight. So it kind of pretend like it's less frequent than it actually was. If we compute the, if we write out the expectation here, we now actually get our expected reward, what we want. So we get our unbiased estimate. And the quick version of why this happens is, before, if you remember, this propensity ended up here in this equation. But now, because we're already dividing by it in the estimator, it doesn't show up in the estimator anymore. However, the main issue here with inverse propensity scoring, aside from the fact that you have to know these propensities, is that you can get very high variance, especially when the propensities are small. Why does this happen? If you have a very small propensity, you take one data point and you give it a lot of weight, and you can think of that as the opposite of averaging, right? If you have a lot of data points, you can average away noise. What we're doing now is taking one data point and we're pretending like it's a lot of data, and thereby inflating the noise. And that's one way to think about where this variance comes from. So that's inverse propensity scoring. We've most of the talks sort of talked about this method that we've seen today, talked about methods related to this kind of approach. But there are some other approaches as well. And the one I want to talk about is the doubly robust method. But before we get there, I have to talk about the direct method. And this is actually also very common, but it's very often not called the direct method. The idea here is that we have some form of regression that's going to predict what we want to estimate, which is in this case the probability of an interaction. So that's represented here by a magic wand, but you can think of this as any sort of model that uses features to make a prediction. So this can be your half of a two-tower model, or some output of your click model, anything that takes in the features of an item and then predicts the click probability or the interaction probability. And using this model, I can now just make a prediction for every item. So I don't have the selection bias problem anymore, because I now have a value for each item. The problem, of course, is that I'm not observing the actual probabilities. I'm trusting on my regression model to be correct. So that's why I chose a magic wand here. So I'm using it like magic. I'm kind of, I'm just relying on this model completely. It might be a very reliable model, it might not be, but from the point of view of the direct method, we just have to trust it. And then what I can do now is I can just link it to each of one of the actions, right? I no longer have a selection bias problem, in the sense that I have a value for each of the items. The problem now is that I don't know if these values are actually correct. So we've now gone to the other extreme, which is, so to show that in notation, right? I can now make a summation over all actions. So I'm still using my data points for the context in this case, but I can sum over all actions. And then here I have this P with a hat. And the reason I give it a hat is because it's not the real probability. It's what my model predicts as the probability. And I can just use that for all of it. So I don't have the selection bias problem. But you can clearly see, for this to be unbiased, for this to be correct, right? I actually need this probability here to be the real probabilities in all cases. So what I'm actually asking now is to have already solved this problem, right? If I already know the click probabilities, I don't need to estimate them anymore. So to be completely unbiased here, we already need to have solved the problem. So we can't really, we shouldn't expect to be unbiased here. But what this is really about is that we've now gotten rid of all the variance. So we're almost certainly somewhat biased, but maybe not that much if our regression is very good. But we no longer have any variance from the interactions, because we're completely ignoring them. So where IPS had this unbiased property, but high variance problem, here we have no variance problem, but we almost surely have a bias problem. So we've gone to the other extreme. Now, the idea of doubly robust estimation is to combine these two approaches to sort of get the best of both worlds. And the main intuition, or the main insight here that's being used in doubly robust estimation, is that you can actually start with a direct method and then use inverse propensity scoring to unbiasedly estimate your error. So let me show you how that works, or what that might look like. So here we have the same setup again. I am using inverse propensities because I'm still using IPS, but now instead of estimating the click probabilities, I want to estimate the difference between the click probabilities and the predicted click probabilities. So I'm actually going to take this interaction, and then before I link it to any action, I'm going to look at what did my model predict and what did I observe, and what was that difference. So this is what is the error that I get from the direct method, basically. So is this if we see an interaction but we predicted a low probability, then we probably made an error or an overestimate of the click probability. Vice versa, if I didn't see a click but I had a really high predicted click probability, I made maybe the other way around. I made an overestimate, and otherwise I would make an underestimate. Either way, this shows us in which direction we're making the errors. And we have the selection bias problem here, but we're using IPS to correct for that, so we still need to use IPS. But this picture here now gives us the unbiased estimate of how wrong the direct method was. So what we can do now is we can basically just combine them by addition. So what I'm doing here in this top equation is I'm starting with the direct method. So that's the one where we only use regression. So we just ask a regression model basically, what do you think the performance of this policy is? Then based on the data the interactions I observe, I'm now going to have an IPS estimate here. So again, IPS to correct for that selection bias in this data. But instead of the actual interaction, I'm taking the interaction minus the predicted click probability or the interaction probability. So this here is now the difference between what we observed and what we predicted. And in expectation, this is going to work out. Why, right? I didn't have that here, but the reason it's going to cancel out is this part, these predictions here are going to cancel out this part of the equation, and we're left with the IPS part of the equation, which is unbiased. So in expectation, we have an unbiased estimate here. You might have seen this before, but you probably have not seen it written out like this. So this is something that's going to be useful later. You can write this down as the direct method estimate, plus the IPS estimate minus a covariate. And this is not how it's usually described. It's going to be useful later when we want to create a new double robust estimator. Yeah, so the reason why it's called doubly robust, and the neat thing here is this estimator is unbiased if for each item either the inverse propensity is correct, so the propensity by which we divide, or the regression estimate is correct. So either this value here or this value here needs to be correct. It's an OR relation, so you only need one for each item. Whereas for the other estimates, you need either all of the propensity to be correct or all of the regression estimates to be correct. Now for each item, you just need one of them to be correct. And you can also prove that this has less biased if the regression is somewhat decent. And it can decrease variance. So if I write out the variance, we now have the variance of the IPS estimator plus the covariance minus the covariance between these two. And if they have covariance, you can actually get less variance than with the IPS estimator. Okay, that's my brief overview of these methods, right? We started with inverse propensity scoring, the method I think which you heard about most today, where we reweigh observations according to logging policy probabilities. They're unbiased as propensities are correct, but you can expect high variance, especially if you have low propensity actions. Then there's the direct method, where you purely rely on some regression estimates. So you have some model that uses features to predict these interaction probabilities. You can expect this to be biased, because you really need your regression to be 100% correct to be unbiased, but you have very low variance. And finally, I showed you the doubly robust estimation, or the doubly robust estimator, which starts with the direct method. So we start with just a regression estimate, and then we use IPS to correct for that mistake of the systematic mistakes of the direct method. And it's much easier to be unbiased here. And we can also have lower variance than IPS, given that the regression is somewhat decent, which is in many cases very much doable. So this is what it looks like sort of you could say these are the main families in general counterfactual estimation. In the learning to rank field, most of the work was talking about inverse propensity scoring. So I'm talking up until about a year ago. There was some work using the direct method, but usually they call it a click model or something like that. But so they didn't have the right name, but if you follow what they were doing, it was pretty much the direct method. But we were lacking doubly robust methods. What I want to do in the rest of the talk is now explain why I think it was so hard to get doubly robust estimation to work for learning to rank, or for ranking, or position bias to be specific, and how we can actually get it to work. But the motivation here was, why is this difference here? Why are we stuck with IPS for so long in the learning to rank field, when outside of that we have also these other options? Okay. All right, so let's get to the ranking part. So you've already seen quite a lot about ranking today. What I mean when I talk about ranking, or the ranking setting, or the ranking problem, is that we're not just going to show one item, we're going to show an ordered list of items. So we're going to show multiple items, and users can interact with one or more of these items. Our goal is to maximize the total number of interactions, right? So you're going to show a ranking, you want as many clicks or as many purchases or watches or whatever there. Very common in search engines and recommendation systems. Or, well, I would say this is practically every search engine and very common in recommendation systems. Right. So the first thing you run into with ranking always is this combinatorial problem. I know these numbers for a very long time, but it still amazes me every time I see them. This is the number of possible rankings for the number of top 5 rankings you can make out of the different numbers of candidates items. And so if you want to have 1 million different rankings, top 5 rankings, right? All you need over here is 18 items. If you want, what's this, 1 billion, or is it 100 million? 100 million, sorry. You only need 42 items to reach 1 billion, or you don't need that many more, but you get the idea. So the number of possible rankings here grows at an enormous rate. If you remember from the other methods, we needed a propensity that was the probability of taking an action. If each ranking is its own action, we know these propensities are going to be extremely small, right? So you can expect to see at least a propensity of 1 in 1 million if there are 1 million possible rankings, and probably you're going to see a lot that are a lot lower. These tiny propensities mean a huge variance. So applying the normal, the generic counterfactual estimation methods directly to rankings, seeing each ranking as an action, is just not going to work. So we need a different approach. And one of the ways to deal with this approach is through seeing position bias as selection bias. So instead of thinking about selection bias in terms of actions, we can also think about it in terms of interactions. And this is inspired by what's known as position bias. So what you see here on screen is where people look through an eye tracking study, where people look on a screen if you show them a ranking. And what it shows us is that almost 100% of people look at the top 2 results. But if you go down to, let's say, result number 8, you have less than half of the people are still looking. So if you think about what that does to a click-through rate, if you see a low click-through rate up here, that probably means users don't want to click on that. But if you see it down here, that might just mean not that many people looked at the item to begin with, right? So this position bias is going to have an effect on the clicks that we see. And again, this is bias, this is not noise, right? So this figure you see here is an average over a lot of data. It's not that if you get more click data, this disappears. It's a systematic problem, so it stays. So you need a way to deal with it. And the first step that we deal with this in the field is or one of the approaches to deal with it that I'll talk about today is to first model this relationship between, we have to make some assumption where we model the relationship between clicks and the quality or the relevance of an item with some sort of formula that's preferably, it has to be usually invertible. And we then derive an unbiased estimator from that model. So for this work, I'm going to use the following. So I'm going to assume a click depends on an item and a position. So what's the probability of an item being clicked given that you displayed in a certain position? And here we have the relevance of the item or the quality, depending whether relevance is the right word in the context. So how good the item is basically. And the relation between these are based on these 2 parameters, these 2 bias parameters. We have the rank-based correlation and rank-based trust. So I'll start with the second one, the beta parameter. So we call this the trust parameter because what it says is that at each rank, so K again is the rank, right? This is a parameter for each position. What we're saying is at a rank, users give you clicks regardless of how relevant you are. So especially if you're a big search engine, people are going to click just because the search engine put it at number 1. If you type something into web search and it gives you something and it doesn't look right, but it's at number 1, there's a lot of people who will still click on it because they think, well, if it's number 1, it must be right. So you can think of that as sort of the base rate, or I like to think of it as the clicks you get for free just for being at a certain rank. Then the alpha parameter here is how many more clicks do you get if more people, if you are more relevant. So this captures sort of this, both of these capture some part of the position bias, but this captures the part we usually think about. It's like how many people look at a certain rank. And at the top of the rankings, these parameters are usually higher values. So there's you get more clicks. So being more relevant gives you more of a correlation usually. At the bottom, these are usually very small numbers. And importantly, we can invert this formula. So if we want to know the quality of an item or the relevance of an item, and we know the click probability, we can subtract the beta parameter and divide by the alpha parameter, and we have the relevance probability. In sort of the earliest work that talks about this idea, they don't have the beta parameter. So this is work from 2017 where Thorsten is the first author. And they only have the alpha parameter. So there, it really works like a filter. So what we can think of, this is closer to the figure I showed you before. So what we can think here is that at the top of the ranking, where everyone looks at a position, you get 100% of the click-through rate. So you have like a multiplier of 1. But at the bottom, where let's say 40% of users look at a position, you only see 40% of the clicks. So if you want an unbiased estimate, you're going to have to multiply it by 1 divided by 40%, or 0.4, which is 2.5, right? So if 10 people click down here, I can pretend, oh, those were actually 25 people, would have been 25 people if I had shown it up here. That's the assumption that we're making here. And this is the basic idea behind sort of what I call exposure-based position bias correctly. So the main point here is that this is the same idea as we saw in inverse propensity scoring before, but now instead of basing the propensities on actions, we're basing them on this exposure. And the reason I'm doing that is because the exposure values are much greater usually than those action probabilities. So instead of talking about 1 in a million, we're maybe talking 1 in a few hundred. And that order of magnitude difference allows us to deal with the variance. The difficulty now is, of course, that we need to know these exposure parameters, but there are a lot of ways to do that through randomization or expectation maximization based methods. Okay, let's build the inverse propensity scoring estimator here. So I'm going to start by introducing the propensity based on exposure. That's going to be my row, where remember D is the item, so this is item specific, which is based on the expected alpha value. So remember, alpha was a correlation between clicks and relevance at a rank K. So I'm going to say, okay, how likely is an item to be placed at a rank according to the logging policy, and what was the correlation between the relevance and the click probability there. So this row is really the correlation between relevance and clicks, but now on the logging policy level, not for a specific rank, right? So that's my correlation between relevance and clicks. What I can do now is to create the position bias IPS estimator with trustwise corrections. Is I can average over my data. For each click, I'm going to subtract the beta parameter at the rank at which it was displayed. So what I'm basically subtracting here are the clicks that this item got for free, right? So if it was displayed at the top, we expected to get some clicks for free. We're subtracting them here. And then whatever's left, I'm dividing by this correlation, because that's going to tell me so I'm dividing it by the correlation between clicks and relevance. So we're moving from the click space to the relevance space, how you can think about it. And except for like, if you ignore this beta part here, we are looking at something that's basically using the same idea as the standard inverse propensity scoring, but we're avoiding these really low propensities. And it's unbiased. If this propensity is correct, this means we need to know the alpha, beta, and the logging policy. And alpha and beta are new here, but again, that's a price we pay for being able to do low variance estimation. Okay, that's what inverse propensity scoring looks like. Now let's go to doubly robust estimation. Now, if we try to apply doubly robust estimation, you run into some problems. And I have to speculate a little bit here because I don't know what other people were running into, like what they were thinking, right? But I wanted to answer the question, why haven't we seen this exposure-based variant of doubly robust estimation that we do have for inverse propensity scoring? And what I think is the main problem is that what we were using in doubly robust estimation is the difference between what we were predicting and what we were observing, right? If you remember, we were observing a click and we had the predicted click probability, we're looking at the difference. In the learning to rank estimation, we're actually working now with relevance instead of clicks. So what we would need if we were to directly apply standard Doubly best estimation is the difference between the predicted relevance and the true relevance. However, we never observe the true relevance. We only observe clicks. So we never have this difference between true relevance and observed relevance. And that's why you can't just take Doubly best estimation and plug it into this setting. So I believe this is sort of the main hurdle that we have to overcome. For the direct method, it actually turns out that you can do quite some things to get an estimator working. Again, you can use any regression estimator, but if you want to optimize such a thing, here's an example. I won't go into too much detail, but you could unbiasedly, for instance, estimate cross entropy loss. So the first work that I found on this work is actually from the people that are listed here, Becker, Robrecht, and Davis from 2019. I believe in the same year or year later, Yuta Saito also did a paper on a similar idea. But the main idea is that you can use IPS to estimate cross entropy loss, and then you can use cross entropy loss to optimize a model. So that way you can get a regression model that's hopefully unbiased, at least based on an unbiased estimate of the loss. So we can solve the regression problem, so we can get the direct method. The question is now, how do we get from IPS in a direct method to a Doubly best method? And this is where this different notation came in. So what I realized is that you can rewrite the Doubly best estimator to direct method plus the IPS estimator minus a covariate. And we know what the direct method is easy, right? That's trivial to, if you have the regression model at least. We know what IPS should look like if we use these exposure-based propensities. So the question was now really all I had to solve was what should the covariate look like? And what we know from the properties, it needs to have the same expected value as the direct method. And we want a high covariance with IPS. Now, starting from there, what I found out is basically the following. So this is what the covariance should be. And admittedly, this looks, when I first found this, I was confused what I had found and what we're looking at, but I'll walk you through it, right? So what's happening here is we're going over all our data points, so all our interactions, but instead of looking at the click, it's just looking at the correlation between the document's relevance and the document's click probability at the rank at which it was displayed in the data, divided by the expected correlation under the logging policy, multiplied with the this is the output of the regression model, so the regression predicted relevance estimate. So what you can think of this as how much more or less correlation was there in the data between click and relevance than you would expect under the logging policy, right? So the ratio between the correlation that we see in the data and the correlation that's actually there in expectation of the logging policy. This is certainly to show that this is an unbiased estimate of the direct method, because if you remember, this propensity was just the expected value of alpha. So this just turns into 1, and then you have your direct. So we can see that this is unbiased. So the question is now, what about the covariance? And something really interesting happens if you plug this, if you write out the formula that we have up here, right? So when I did that, I suddenly realized what was going on. What's happening here is that we're using the difference between the click we observe and the click we predict, and then work our way back to relevance. So again, the Doubly best estimator here starts with the regression estimate for relevance. So this is where you ask your model, based on the features of this item, how relevant do we think it is? Then we go over all our data points, and here we have an IPS estimator. And again, because we're dealing with position bias in this case. And then, but in here, instead of just a click, we now have the click minus the predicted click based on the position at which the item was displayed. So we show the item somewhere, and we say, on this position, what was the item we would, the click probability that we predict here? Did we actually see a click or not? And that difference is what we use here. And you can see now that if our regression model is very good, then we would expect a high covariance, because we are predicting the clicks. If we're good at predicting the clicks, then these values are going to be small. We have the covariance here. So yeah, again, so the way to think about this is we're looking now at the difference in, do we see more or less clicks than we have predicted, and then using our exposure-based IPS to work our way back to relevance. All right, so to be unbiased here, we need alpha and beta to be accurate. That's the same for all of the methods in the counterfactual learning to rank field. But for each item, we either need the correct logging policy propensity or the regression estimate needs to be correct. So either we need to know what the logging policy does with the item exactly, or this estimate over here needs to be correct. As far as I know, but this is a hard claim to check, this is the first Doubly estimator that doesn't require directly observed errors. I couldn't find one where we're using a different kind of error to correct for a different error. Okay, there's a couple things we can prove here. So one of the things is that if our regression errors are in this range, right? So if our regression estimates are between 0 and twice the true value, we provenly have less bias and or equal bias and less variance than IPS. Again, we still need to know alpha and beta. And so we have cases where there's definitely less bias or equal bias and less variance, or equal variance, I should say. There's some caveats. So if for some reason, for instance, if your policy, if the logging policy and the correlation under the expected logging policy and what you observe in data is always the same, that this reduces to IPS, but this usually doesn't happen either because you have some sort of toxicity or you have some propensity clipping. But it's a caveat I did want to mention. Okay, I've shown you a lot of mathematics here. I want to also give you a bit of intuition to understand why this works so well, like, what we're doing here. So if we think about inverse propensity scoring in this setting, we usually can't display all items, right? So here's a top 4 setting. We only show the top 4 items to users. So whatever happens, whatever clicks we observe, we're only going to re-rank the top items, because IPS, if it doesn't have a data point, it just estimates 0, right? So for item E, F, G, and H here, we know the estimate's going to be 0 because they cannot be clicked, and IPS only reweights clicks. So we know these items are going to end up at the bottom of the ranking for sure. And this has been one of the reasons for this high variance. If items are unlucky and they never made it, they were never shown in the data set, they're just going to go to the bottom. It's a ranking, so that means other items get pushed to the top. So an underestimation of the relevance of one item has like a big effect on the whole ranking. The direct method didn't have this issue, right? The direct method, we can estimate, we can get an estimate for every item, so we can re-rank whatever we want, but we're now ignoring the clicks, right? So we're again trusting on this regression model. You can think of Doubly estimation as starting with your regression model, saying, okay, I want to follow my regression model, how should we rank things? And then using your clicks to update that ranking again. So the clicks can't update everything. They can't move, again, they can't move the items that were never shown, but they can move the items that were shown, and they are better, they are actually, indicated of the true underlying relevances, where the regression model, we don't know whether we can trust it. So this isn't exactly how it works, it's intuition, but I think it's a good way to think about it. Starting with the regression model that re-ranks everything, and then using your clicks to update that re-ranking again. Okay, I'll wrap up with some experimental results to show you how sort of what the performance I saw in simulations at least. So these are simulations based on commercial search engine data sets. This is work from the university, so there's no way I could do any online experiments there. We have simulated position bias and noise, and I'll walk you through the rest. So this is a setting where we can only show 5 items at a time. We don't know the exact biases, so we also have to estimate the bias in here. I didn't talk about that in this talk, but I'm using existing methods to estimate the position bias. And that gives us a plot like this. So the x-axis here is the number of queries in the data set. So this is basically how big our data set is. This is n. So how many observations do we have? And if you get more or less observations, what happens to your performance? Then the x-axis, the y-axis here, you can think of it as NECG. It's not. I argue this is slightly better in this setting, but it's the same idea. Like how many relevant items are at the top? It's in this case actually the expected number of clicks on relevant items. But you can just think of it as the higher the better. This here is the logging policy performance, and this is a full information performance. So this is the skyline. This is the best performance you can get. It's a simulation, so I know this value. And what we see here, the pink line is if you ignore position bias, you get stuck somewhere. This is typical for bias performance, is that you can get more data, but at some point you're not going to improve because you're converging on the wrong optimum. The IPS performance is this green line, and you can see that it doesn't reach full performance even after 1 billion data points. I know in this setting that the bias estimate at this point is very accurate at this when you have this much data. So what's really going on here is variance. It's at this point, this method is really unbiased. It's just there's so much variance that even after 1 billion data points, it can't solve this problem. So that's how bad the variance problem can get. Of course, this depends on your logging policy, but the logging policy here was quite realistic. As you can see from the performance, like it has a lot of room for improvement. But even here, we can't get the optimal performance. Then this blue line here is the direct method. What I did here is I used this IPS estimate of cross entropy loss to train a model and then use that model in the direct method. And you can see in this setting, it does much better than inverse propensity scoring, but it's not provenly unbiased. And you can still see that it has quite large variance still. The Doubly bust estimate is this red line, and is basically, except for this starting point, it outperforms all the other methods and it outperforms them significantly. If we take inverse propensity scoring as the previous benchmark or state of the art, then we can actually see that to get the same performance, we need we have like 1,000 times less data, more than 1,000 times less data. So it's a really order of magnitude difference in how much data we need in this setting to get that performance. This is on a Yahoo data set. I also had a Bing data set. Results are pretty similar, but there is this initial period of bad performance. So there is some risk, and this is basically because it's following a regression model here that's very bad, and that can make things much worse. But as soon as it's decent, again, you see this big improvement. To get the performance of IPS at 1 billion, again, we need less than, this is almost a difference of 10,000, factor of 10,000. On Estella, this is an Intellia search engine that released a data set. What's interesting is here, IPS and the direct method have similar performance, but still we have W bust outperforming it significantly. So that shows us that even if these methods seem to be performing the same way, because they're estimating it in a fundamentally different way, they're making different kind of errors, this combination still is beneficial. I'll say shortly about this initial period of bad performance. A PhD student of mine, Shashank Gupta, actually worked on how to deal with these kinds of risks, and we've published this at CKR. There's a poster about it there at the right in front of me, so we can talk about that in the poster session if you'd like. So there's a way to deal with that as well, but that's not part of this paper. Okay, I want to also show the full ranking setting. So this is a setting where all items can get a click, like in a search engine where users can scroll everywhere. This is more similar to the earlier counterfactual learning to rank work. In this work, IPS actually does reach optimal performance. So that also shows why initially this high variance problem wasn't very well known in the field, because this is where we were testing it. Interestingly, now the direct method has a bias problem or a convergence problem, as the theory would predict. So we see that it really gets stuck somewhere under optimal performance, but it has very good initial performance. And then the Doubly bust estimator is almost like a maximum plus a bit extra. So it's always better than one of these two, and it outperforms them almost everywhere, not here at the end, of course. MSLR shows, again, a different trend, slightly different trend, Estella as well. In all of these cases, we see Doubly bust estimator is almost like a maximal operation plus something extra. It also works if you so here my bias estimates were quite correct. I also tried a setting where I intentionally get the bias as incorrect as possible, and we still see this improvement over Doubly bust estimation over the other methods. I'll skip over that for now because I want to wrap up. So what I would like you to take away from this presentation. First is position bias. Be aware if you work with interactions with rankings, position bias are going to infect your rankings. And if you ignore them in your evaluation and optimization, you're going to have a problem. The main existing solution or one of the main existing solutions, I should say, was to do inverse propensity scoring based on exposure to deal with this position bias. But this had a high variance problem. What I contributed in this journal paper was an exposure-based doubly robust estimation method, so for learning to rank specifically, where we provenly have less bias and variance with decent regression. In simulated experiments, we see 1,000 times data efficiency, at least in top 5 settings. These, I have to say, I've never seen these kinds of results before. Usually, the gains you get are much smaller, so it's quite significant, I think. But what I also think this means for the larger field is that we now sort of can do state-of-the-art counterfactual estimation for counterfactual learning to rank in this exposure-based way. So this opens the door. In the general field, we have a lot of different double robust estimators or methods based on the robust estimation. And now we can sort of start exploring this as well in the counterfactual learning to rank field. Thank you for your attention. Here again is the link to my to the paper, and I'm happy to take your questions.
Thank you. Thanks, Harrie, for the interesting idea of. I think it's definitely a non-trivial way of defining W worst, and also a nice, useful introduction to the counterfactual estimation in general. I do have a couple of questions, but before handling mine, any questions?
There's a question in the back. Do we have a student? We lost our student volunteer that runs with the mic. So
thanks for the very interesting talk. Maybe I missed it. What happens if beta is 0? Like if user doesn't want to click?
Oh, if beta is 0, so beta was the trust bias parameter. So that doesn't mean users don't click, but that means that there's that they don't
intend to click on something.
If they don't click at all, that means both alpha and beta are 0. So
only beta is 0. Like imagine
okay.
it's like
Yes, yeah.
Want to find a document on ads people.
Yes, yeah. But that means okay. So the beta parameter means that if it's you can think of it as if it's completely not relevant. Like if relevance is 0, there's no clicks. That's fine in this method because our estimate will be 0, and that's what we want because it's not relevant at all. Like if I'm predicting if my assumption is the relevance of an ad is proportional to the click probability, right? And there's no one's ever going to click on it, then that means it's not relevant.
Yeah, I guess my question is like, is there any additional value in using your method? Is like beta is 0, or should I just go with like standard approach and it will work, right?
So if you don't like the trust bias part, so in the other talks and most of the other work actually ignores this, doesn't like this either. You can just set beta to 0 and everything else works out still. So your formulas are going to be a bit smaller, your proof is going to be a bit shorter, but everything still works in that setting as well. So this includes both. So alpha and beta, when you add them up, they have to be greater than 0, at least on one rank. So there has to be some correlation somewhere between items and clicks. As long as that's the case, then this should work. Yeah. Thanks for the question. Yeah.
Thank you for your report. I have a question. You said that even if you mess up the alpha and the beta very hard, the model still manages to perform better than some of the baselines.
Yes.
So what exact information does the model get then?
Yeah, I'll show you an example just to be clear what I'm saying. So here, these striped lines here are the same methods, but now I assume that the bias parameters for each rank are the same. So that means we show 5 items and we pretend like every item gets the same amount of attention in that case. So I ignore the fact that at position 5 in a position you get much less attention than at position 1. So and what we see is that performance is much worse, obviously, because now we added a lot of bias, but we still have less bias with the double robust estimator than with the other estimators, at least as far as the sort of empirical things we see here goes. So it's still seeing the clicks, it still knows these items were displayed in top 5 and these weren't, but it ignores the difference between the ranks within the top 5. Okay. Yeah, thank you for the question. Yeah.
Yes, thank you for the talk. I'm interested in how should we calculate alpha and beta? Should we do just linear regression, or is it a statistical method? How to find them?
Yes, yeah. Yeah, I intentionally ignored it for this talk because I only had 50 minutes. There are, so if we assume beta is 0, you can use something that does randomization, so you can randomly swap items and then look at the click-through rate differences. If beta isn't 0, I think right now the only thing that we have is expectation maximization based, so EM-based method or regression EM-based methods, or maybe things like two-tower models can also handle it, but we're talking basically maximum likelihood kind of estimation. Yeah, but there are separate works on that. If you if you go to my website, Google my name, you can find a talk on that. It's basically what's called trust bias. Yeah, so it's a good question, but it's a topic I had to skip today. Thank you for time.
Yeah, I know there are some other questions over there, but due to time limit, maybe we'll go on to the paper presentation. So if you have any questions, you can talk to Harrie after the session during coffee break.
Yeah, I'm happy to discuss your topics online. I would like to say before I go off stage is if you like this topic and you're looking for a PZ position in this kind of work, then please find me, because we have an opening coming up soon.
Yeah. Thanks, Harrie, for the great talk. So next we have 2 paper presentations, and the first one should be very relevant to the topic of the tutorial, double clipping, less bias variance reduction in off-policy evaluation. So whenever you're ready.
Thank you very much. Yeah, so this is double clipping, not doubly robust. So there's double, but it's not exactly the same stuff, right? But yeah, it's still about like a new sort of way of doing offline evaluation. But it's less, it's very much work in progress, and it's not, I think the talk is not really about this method in particular, and I'm not showing like extensive results that it's outperforming other things. So it's really about like an observation on an existing IPS method, namely clipping, and hence later we will do double clipping. But I guess this observation then will provide an opportunity to improve that that widely used method, which is clipped IPS, and double clipping is then just one way of exploiting this property basically, but there might be better ones than other ones. So I'm really focusing on this existing estimator and just giving this sort of as a idea, like double clipping is then one idea of how we could maybe use that. But yeah, so now we had like an awesome introduction to the entire setting. I will go very quickly through my introductory slides, but just to rebase sort of in which kind of setting of the ones that Harrie presented we are. And so for the purpose of this talk, I'm focusing again on like this single item recommendation. So not ranking, we're going back to single items, or the first half of Harrie's talk. But because IPS estimators, also as Harrie said, are really widely used for also ranking slate recommendations on, and clipping, the thing that I'm going to show you in a minute, is really widely used for different settings. And so I guess also like the work presented here will also apply to these other settings. So in this case here, we just have, I'm putting it to the Amazon Music domain again, like where we might have different albums and we want to just recommend a single item to the user, right? And we are always talking about some sort of reward, which we can think of as a click or as like a certain amount of time that the user actually listened to the music. And well, often we have this one method, this one policy or recommender system. Now researchers came up with a new method we implemented, and we want to know, of course, like what would be the reward, the average click-through rate or something of that new policy. And one way would be to do A/B testing, but this is expensive. But what we do have is actually we have some logging data, right, from our running production system, and offline policy evaluators just take this logging data and use and the new policy, and we again the goal is to estimate the reward of that new policy. So yeah, here just once again, and just to rebase sort of notation, I think it's exactly the same, but just to be sure, this inverse propensity scoring is really yeah, is reweighting the rewards that we have in our logging data, so in the data that was collected by the logging policy, and it's reweighting by this propensity ratio that Harrie and others talked about extensively. And also, as we already know, oh, something's missing there. Wrong order. So this is under very mild conditions. This is usually unbiased, but as we know, if pi 0 here, the logging policy weights, if they are very small, then these weights here become really quite large, and then this can lead to a high variance, because then we have not very often we have these huge values, and then it depends on the target policy whether we activate these values or not, and then yeah, we get these huge variance estimates. We see it in a minute again. And so now this clipping, which hasn't, I think Ben in the morning very quickly talked about it. It's really one of the, well, in a way, the most naive and the least elegant method of trying to reduce this variance, right? And what it's really doing is just, well, our problem is high importance weights. So what do? We just clip them off, right? And so this introduces a new hyperparameter, which we call the upper clipping constant, which we then have to tune. But even though we have to tune this is a big problem. It's extremely simple to implement in an existing system, because it's really just adding this single sort of. We don't need to do any of the other things like estimating a reward model for doubly robust and so on. And it's also very widely used across what I said in the beginning, that here we focus on the single recommendation case, but you can also use it for any sort of IPS style estimator, and all of them have high variance, and you can just use it. It's very universal, and I think in practice it's still very widely used. So how does this look in practice? What you see here is data from a very simple standard multi-unbanded kind of synthetic experiment where we have two policies, right? And on the y-axis you see the rewards, say click-through rate. The red dashed line is the true reward that we want to estimate of our new target policy, and the gray dotted line is the logging reward that we saw in the in the logging data. And now we have this IPS estimator, and on the x-axis you see for different clipping constants, right? If the clipping constant is very high, say infinity, here 100 is enough, then it will never actually clip any. In this particular case, it won't really clip any weights off, and so we recover basically the normal IPS estimate. And in this case, what you see here on the right, so this is repeated over, I think, 100 repetitions, and variance here really is this part here, right? So on average, you're unbiased, you will recover the true target reward, but depending on your on your data sample, you might also end up here or here. And if you say compare different policies with each other, different target policies, then this might make a huge difference. So we want to reduce that bias. And for clipping, so basically moving from right to left here, we're reducing the clipping constant. And what you see is that, well, you reduce variance, right? Sort of these error bands become smaller. But you also see that, so the average line, the average blue line is, well, the average estimator will get more far away from the true reward, which is then the bias, right? So it's very clear here that reducing, moving U towards 1 will reduce variance. That's what we want, but it also will increase bias. Now, this is, you might say, oh, this is the normal sort of bias variance trade-off, but I think, so this is sort of the observation that I'm trying to focus on here. It's a bit different than, say, L2 regularization, where you where you also have like a bias variance trade-off. So you have to find, well, the best bias variance trade-off, but it's always you reduce variance, you increase bias. There's one difference here, I guess, is that this blue line, so this is just one example, right? One synthetic data experiment. But this blue line will never go up. It will always show something like this. It will always go down because you're always clipping from above. So you will always have this downward bias. And I think that's something we can exploit because, yeah, again, like if in other bias variance trade-offs, you don't really know where the bias is going. And that's why you can't really do anything with it. You pay with that bias in order to reduce the variance. Now here, you could think, well, if we always know that that we have a downward bias, why can't we increase like an epsilon? Then we would be already a bit less biased without really without hopefully re-increasing the variance. And that's sort of what this is based on. And so we can show, again, this was just an example, but we can also show it. I won't go into the details here, but in the paper, like it's a very simple expression that just shows that this bias that I just talked about is always negative, like it negative for 0. And so, yeah, again, so double clipping is now just one heuristic, one hack, you might say, to try to counter that bias and to compensate for that bias while without re-increasing variance, right? So that's the goal, that maybe we can keep variance at the same level or decrease it even further, but hopefully sort of like compensate the bias that we introduced through that variance reduction technique. And again, this is purely heuristically chosen, that just at 1 over L, because, well, we're dealing with these ratios, right? Propensity ratios, but something else could be much better. But basically, just to give you an idea of what's happening. So what we're doing here now is, that was the same experiment as before, but now the orange line shows the double clipped IPS estimator, and it's moving again, heuristic, again, hack. I just said L equals to U, just because to make this graph easier to look at, basically. So I move, instead of only moving, so for the blue line, again, it's only the upper clipping constant, and moves from right to left. For the orange line, we move both the U and the 1 over L basically at the same time. And in this particular setting here, right, you see that, well, also for the orange line, the variance reduces over time, but the bias, it stays closer to the tree reward, because we have this downward bias, and now with the clipping from below, we have some upward bias. Of course, it's a question like how can we balance them? Can we overshoot and then introduce more bias, which I argue is not. We come back to that later. But here on the right, what you see is basically the same. If you look at the error components, so you see variance is decreasing for both. So these are the dashed lines if you go from right to left. But the bias, which is the squared bias in this case, which is the dotted line, will never increase as much as for the single clipped estimator here. There's another nice property, like one that I really like about this sort of clipping above, clipping below, is that once, like this is the extreme case, right? Usually you wouldn't go and clip towards 1, because that's then it's just a logging policy. Like this is, it's what it is. But basically on the way to clipping constant equals to 1, you're sort of, well, you're moving towards the logging policy reward. And in a way, you can think of this as sort of like regularization towards the logging policy. So in case you don't really know much, then your best guess is that your new policy, which might be often it's a very similar policy to your logging policy, right? It's sort of, maybe you have new data or so, or a slightly modification to your algorithm, but usually it's not like a completely new thing that you try to estimate. So if you have something that's very close to your logging data, then maybe it's a good prior, if you want to take Bayesian terms, to regularize towards 2. And yeah. So to wrap up, so I think this sort of knowing the sign of a bias term is something we usually don't have when we navigate these bias variance trade-offs. And so, yeah, I think we could find some way to use it, and maybe better ways than just doing this heuristic clipping from below as well. So maybe we can find something about the distribution of the propensity weights, right? It's usually we know what pi is, usually we know what pi 0 is, we know the propensities. Can we say something about the ratio of the two? Maybe that follows some certain distribution that we can use again to have some better prior information as well. Coming back to a point that I made before, like you could argue, okay, if I clip too much from the bottom, then I might overshoot and like the bias may become positive. But it's sort of, you have to overshoot by a lot in order for that to happen, right? You have sort of, you reduce variance to introduce some bias below, like downward bias. Now, for a very long time, you're actually compensating, you're becoming better. And then maybe if you overshoot a bit, you're becoming worse again. But if you like, in order to get worse than what you had initially, like the first downward bias, you have to go like 2 ways basically in the other direction. So I think it's almost like very difficult to get to that case. Now, well, what I presented wasn't really actually like something that you could just use, right? For that to happen, we also have to come up with ways of selecting these hyperparameters. So that's a huge part missing here. And there's a lot of interesting work on that from Udagawa. It was actually presented, like now it's AAAI, but like I think it was presented here last year in Seattle in the same workshop. So that's really cool. And yeah, I think there are ways to sort of tune these clipping constants. And then lastly, I think, so I repeatedly said, yeah, it's sort of a heuristic how I chose it. If you look to sort of position bias models and do the double clipping there, then actually this U and 1/L way of clipping has some nice, interesting interpretations in terms of what it does to the position bias model and what it actually means. But please, if you want to know more about this, please come to talk to me at the poster. And with that, thank you very much. I'm happy to take any questions.
Thank you for the talk. We have time to take one big question from the audience.
Do you have any intuition on how to select the 2 clipping constants? Seems from your experiments when you said U equals to L equals to 10, that give you the lowest bias, but not sure like how that's true in general.
No, I don't think it would be true. Like, so I think what will happen in practice is, if I'm talking about like limited experience from our use cases, like using different but other clipping methods, is sort of that over time as a lab, basically, if you're working with the same problem over and over again, you sort of get a feeling of where good clipping constants are. But that's very hand wavy. Like, I don't think there's like a general clipping constant that is good to have, right? Like, it really depends on how randomized your policies are, like where you expect your ratios to be. But we do have some information about that. That's what I was saying, right? Like, usually in order to do IPS, we have information about pi and pi 0. So maybe, and usually also this comes with information about the distribution. So maybe we can get to some sort of good guesses by looking at these distributions and looking at how the ratio of these two distributions behaves. Basically.
But in real data, we don't know the true values like expectations. So it's kind of hard to balance.
The true values of what? No, that not, but of the propensity ratios, right? It's sort of almost, it's not completely independent of the reward, but we're really interested, like we're clipping only the propensity weight ratios. And so I think, yeah.
Okay, so then thanks as speaker again. Coming up is the final content of the session. And the presentation is going to be via Zoom.
I think so.
Yes, hello. I don't know if everyone can hear me.
Yeah, we can hear you. We can't see you. Yeah, we can see you now as well. Could you share your slides?
Yes, coming up. Is it okay?
Yeah, well put. If they're full screen, yeah, looks great. Thanks.
Well, hello everyone. I'm Minmin from Criteo AI Lab. I'm going to present today some work we've been doing within the recommendation team. So first, I'll start by introducing briefly the problem and talk about how we built up from previous work within Criteo, and describe the model and just present some results we have. So the context here is contextual slate recommendation. We want to recommend the best items to a user. When we talk about items, we are mainly talking about tens of millions of products that we will refer to as actions or items in our presentation. And then when we talk about the users, the history of past user interactions usually, or a context of a web page, for example. And then when we want to define what's the best recommendation, that's a bit controversial. So there is non-reward reco and reward reco, non-reward as in collaborative filtering or BPR, and reward when we want to maximize the reward per user, like in bandits or reinforcement learning. In Criteo, we think that the world is a nuanced world, so we think that the best recommendation is actually somewhere in between. So what if we rank the items and optimize the reward at the same time? How to do that is that we want to use the prior information we have, like bidding features, item similarity, user similarity, user item similarity, in combination with the reward signal like clicks or sales. One important thing for us in this research is to work with real challenges in production environments and production data sets. And one main characteristic that comes out from recommendation data sets we have at Criteo is that the reward signal is very uneven. So in the paper, we work with a synthetic data set that kind of recreates this uneven distribution within the recommendations. As you can see here, the signal is actually concentrated in one product within one context. So what we mean here is that we have 80% of the signal we're recommending video game console in the context of technology, and that's 80% of the records we have. If we look at it from the perspective of context, then it's 90% of impressions belong to one context, which is technology. And if we look at it from the context of products or actions, then we have 2-star actions that dominate the records, which are video game console and basketball. It's about 88% of impressions in the dataset. So as you can see, the reward signal is very uneven, and what we want is to be able to use this reward signal when it's available for the contexts and products that are available, and then be able to predict something that is still sensible when we don't have it. So the goal is to use the reward signal in preference of the prior information, like the context distance, the item distance, and gracefully handle the situation when there is no signal for some contexts and actions. One intuitive way to do this within Criteo is to use a likelihood-based model with variational bias. So this is some work that already been explored with 2 papers published within Criteo AI Lab. The Blob paper, which is a Bayesian lattice organic bandit model. It's like a contextual bandit model as a logistic regression that uses the prior information that I was talking about. Here, this is the action context distance, and the action distance, and the context distance. And then another work that's been published a year ago, probabilistic rank reward, that uses an interesting model for the reward here and the ranks, using a categorical distribution and a likelihood production friendly model that actually is now productionized within Criteo. So our main work here is to combine both, because Blob succeeded in leveraging the uneven signal, the uneven reward signal, by use of prior information, and PRR accounts for varying banner size and also uses a production-friendly likelihood. So that here comes our main contribution, which is Bayesian PRR. I wanted to talk to you concretely about what is the item distance in this case. Basically, we're using the mclip embeddings to produce these heat maps and use them in the learning process. As you can see, video game console, for example, is highly correlated with adventure game. And you can see that basketball is highly correlated with an NBA jersey. So this is something sensible that we want to use in recommendation. In the context distance, it's also interesting. Technology and science is highly correlated. Lifestyle and health is also highly correlated. And then there is the item context distance, which is quite interesting. You can see that face cream moisturizer is highly correlated with lifestyle. Video game console it's highly correlated with technology. I'm showing you this because it's important to note to be able to interpret our final results. And this is the model. It's a hierarchical model where, as you can see, we are using the modelization from PRR as a categorical distribution, modelizing the non-reward here. R bar is R is the reward and R bar is the non-reward, and here is the rank of the items within one banner. So it's a banner of size L. Knowing theta zero, we call it a score of no interaction, and here are the actions or items that are shown in the banner. Z is the context, and theta is all the other score interactions within the banner. So the idea is to, of course, is to predict the scores of interactions. We put a prior on them, a matrix normal prior controlled by the action context distance, and we took covariances that are the action distance and the context distance, and we put a prior on this factor here to be able to have a certain control when to override the action context distance here. We adopted an incremental approach, meaning that we started from simple priors, even independent priors, like in the case here. So we're not using the impedance at all. We're just putting a Gaussian prior on the scores of interactions, and then moving slowly into more sophisticated priors to be able to quantify the effects of using such priors and factoring in each distance. How does it affect the results? The second model here is the first time we use the impedance, but with only the action distance and the context distance. It's centered just around 0 without the action context distance, and then the more complicated model with the full distances here, controlled by W, our Gaussian distribution that we learn in the training. So these are the main comparative results. What's important to note is that the blue here, which presents the results of the independent model, is actually just reproducing the uneven signal. So the priors we put here are just uninformative priors. We're just reproducing what is in the data. As you can see, the long error bars, the blue error bars here, just say that this is just a prior. We don't have any reward signal on these particular pairs of actions and contexts, whereas the short error bars here, the blue ones, mean that we actually have signal on basketball within technology, or on video game console within technology. So actually we are sure that the recommendation is somewhere here. And then when we move to using the impedance, then we start to see interesting results, like I don't know if you can see my cursor. So here, video game console, for example, in science, at first we didn't have any signal that we didn't know whether it's a good recommendation or not. But when we're using the context distance now, we are able to predict that it's actually a good recommendation because we're borrowing strength from its good performance within technology and computing, since science and technology are highly correlated. The same thing when we look at items that are similar. So here the cable high speed HDMI is borrowing strength from video game console, because as you remember in the heat map, they were highly correlated. Even though we don't have any signal in our data on cable high speed, we're not able to predict that it's actually a good recommendation within the context of technology. Same thing when we look at items and contexts that are similar, like face cream, moisturizer, and lifestyle. At first, here the blue air bar shows that we didn't have any signal before on this particular product in this context, but now when using the action context distance, unlike the two other models, we're able to predict that it's actually a good recommendation to recommend face cream, moisturizer within lifestyle. So the conclusion here is that we're able to borrow different informations from similar items, while still being able to use the reward signal when we have it, like in the two products here I showed. This is the end of my presentation. If you have any questions, don't hesitate. Thank you.
Thank you for the talk. Again, we have time to take one quick question. Any question from the audience? So I have one question, general question. So I did a paper, and one of the motivation of the paper is basically to do with the slate recommendation, right? In research paper, it's basically from the academia, the main topic when working on slate recommendation is to be able to deal with like the interaction effect between the items in a slate, right? When estimating the value of item A, that the value of item A might be different when presented with item B or item C, right? So that's basically what interaction effect means. So do you have any sense on how important it is to be able to deal with that kind of interaction effect from the practical perspective, or is it actually enough to focus only on estimating the individual value of each item to make effective recommendation in practice? So if you can comment on it from your practical perspective, that would be very interesting.
Yeah, thank you for your question. Actually, it all depends on the data available. So of course, when the reward signal is even and we have enough data for all items, then we don't need to leverage the interactions between the items themselves and the similarity between them. But once the signal is very uneven, as is in the case of some RECO datasets, then in practice it becomes almost impossible to do good recommendation if without taking into consideration the interactions of the items and the similarities between them. So the work here is mainly to deal with this practical challenge and to be able to make a good recommendation even with these uneven data sets. This model now is being productionized within Criteo, and it's already showing good results. So to answer your question, it all depends on the data set itself and the records. If it's uneven signal, then you can't have good recommendation without using something else other than reward signal, because otherwise you won't be able to predict what's good in case of there is no signal.
Okay, thank you. Let's thank the speaker again. And thanks for the session. So after this, we're gonna have another coffee break and also the poster session, and we will be back at 4:05 p.m. Yeah, so thank you everyone for your attention.
Right, I want to thank everyone, both offline and online, again for joining us today. We're already made it to the last session. I can't believe it's almost the end of the workshop already. But we're gonna end very strong because we have another keynote and paper session. And for the final keynote speaker, we have Dr. Wang, who is a research fellow here at the School of Computing of the National University of Singapore, where he also received his PhD from Professor Tatseng Chow. He's done a lot of research on recommender systems, data mining, causal inference, including a recent tutorial on the topic. He's also recently won the 2020. He's one of the winners of the 2022 Google PC Fellowships, and the National University of Singapore's Dean's Graduate Research Excellence Award. And recently at ACM 2019, he was on one of the papers that was in the best paper final lists. So please give a very warm welcome to Wang for his keynote on causal inference for recommended. All right.
Yeah, thanks for the introduction and thanks for the invitation. It's really my honor to give the give the keynote the title of the presentation is causal inference for trustworthy recommender system. The most many content are borrowed from our tutorial this year at CGR. Yeah. So I just go back several some background about the causal recommendation system, and we'll give an introduction for using causal inference for different applications. For example, debiasing recommendation or generalization in recommender system, and some other applications. Finally, I will summarize and provide a present summary open problem and future directions. So as we all know, we are living in an era of information explosion, and the recommender system is a powerful tool to address the information overload. So this is a basic workflow for recommender system. Actually, we have some users, we collect data from these users, and then we do the recommender training. And after that is a servicing stage, and we will serve different users by providing some personalized recommendation, right? So it forms a feedback loop between user data and the recommender system. So one big problem is that during the data collection stage, we will have many biases in the data. For example, because the data is not is observational rather than experimental data, so it's missing, not as random. So based on this kind of biased data, we need to build the recommender system, so the recommender system can be biased by the data issue, because that's a kind of data issue. And also another problem is that the bias is shifting along time, right? So because the user features are changing and the item features are changing, so the interaction distribution of recommendation data will change over time. So the bias is shifting along time. But when we do recommender training, the main task is to minimize the difference between the historical feedback and the model prediction. So we have the input is user and item features. We feed them into a model and to predict the user interaction probability, and we feed this kind of this model by training on the historical user feedback. So in this process, the inputs are user and item features, and the output is optimized to fit the historical data, right? So the first kind, maybe one kind of recommender model is called shallow recommender learning, and after that there are some neural network for recommender system, but they are all fitting the correlation between the input features and the user historical feedback. Yeah. So, but one big problem is that because of the existence of this kind of bias in the data, so the correlation is not equal to the preference. Yeah, so there are three basic type of correlations in the recommendation data. Maybe there are different structure between the variables, and one maybe familiar one is confounding structure. So there are variable affecting two factors. So these two factors might have correlation during the confounding of this factor. So maybe in the recommendation, I give one example is that maybe high quality items, high quality product will have a higher price, right? But this kind of high quality will cause many user purchases on the platform. So maybe there are high correlation between the high price and the user purchase behavior. But this doesn't mean that users will like this app because of the high price, right? It's because of high quality instead of the high price. So this is one example for the confounding issue. So because of this kind of bias in the data, and the data-driven recommender model will learn some skewed user preference, and it will not well reflect the real user preference. So how to solve this problem? One big direction recently is using causal inference to do trustworthy recommender system. And it can help us to understand how the users interact with the platform and how the user feedback is generated. It can help to capture the actual user preference. So our idea is that we can make reliable explainer recognition by considering both the correlation relations and the causality relations. Before jumping into the summer related work in this direction, I briefly introduce several concepts. Maybe summer work will rely on this kind of concept. And the first concept is called structural causal model, and I guess structural causal model is very popular in the causal community. And structural model provide a paradigm to describe the relations between the variables by using a causal graph and summer functions, right? So we can describe these kinds of relations between these variables by using these kind of functions. So there are three basic causal structures in the causal graph. Maybe the Chen structure between three variables. We have the Chen structure. So the Z here, X affects Z, and Z also affects Y. And there is a Chen structure here, and Z is a magnitude rule. And another structure is popular is confounding structure. So we have a variable Z is affecting the variable X and Y. Another one is called colliding. So there are two variables, X and Y. They are affecting the Z. They both affect the variable Y, the variable Z. So this for these two structures, they might cause some severe correlations between X and Y, based on depending on not depending on this variable Z. Yeah. So are there some confounders in recommendation? I guess I will give one example between the quality and the price and some click or purchase user behaviors. And another example might be this one. We have some recommender algorithm, and we use this kind of recommender algorithm to give some recommendation to the users. And so maybe the item position presented in the recommendation list will affect the user click, and also some item exposure also affect the click. So there are also some confounding structures in the this data collection stage. So some confounders are observed, and some one are not. So maybe we need to solve the issues of this observed and unobserved confounders, and some causal technologies can be helpful for this kind of problem. So in the second part, I will give some more instruction for some representing works, and they are because there are many directions in this. Many different problems in this direction. Yeah, so I picked two examples. One is the biasing direction, another one is OD generalization direction. And I will talk a little bit about some other applications in the, lastly. Yeah. So for the debiasing, the most representative bias problem in recommendation domain is called popularity bias. So the recommender model, because the data are biased to some popular items, so they occupy most of the interaction in the data set. So the trend on this kind of biased data, the recommender model will favor a few popular items while lacking deserved attention to some long tail items. Maybe some long tail item have high quality, but they didn't get enough exposure. So in this work, the authors argue that previous method might ignore the underlying causal mechanism by blindly removing the popularity bias and pursue uneven distribution maybe. So, but in their view, they guess that not all the popular bias are bad. And the summer popular item deserves their high exposure because maybe because of the high quality or some other factors. So the platform has the need to consider the popularity for recommendation, but not blindly remove the popularity bias. So actually in the traditional recommender models, we just input the user item features to calculate the matching score for the recommendation, right? This is an output of the recommender model and to fit the historical user behavior. So in the previous peer-to-peer work in the traditional recommender models, they are implicitly modeling the popularity because they are trained on the summer buyers data. So the user feedback favors the summer popular items. So they are learning the popularity implicitly. But in this work, they consider the popularity explicitly. They model the popularity as one additional input of the recommender model. So they calculate the item popularity for each item and model it as an input of this recommender model. So they consider that the item popularity might affect the item representation and also affect the prediction of the recommend model. So maybe some popular items will have a higher prediction score. And for this work, I guess that we can use backdoor adjustments to cut down this backdoor path from I to C. Maybe some popular items will have higher prediction score only because they are the backdoor path here, and because they are popular, so they will have a higher prediction score. They didn't consider the matching between the user and the items. So in this work, they use the backdoor adjustments to cut off the backdoor from Z to I, and to calculate this equation, so we just first to estimate this conditional probability given the user, the item, and one additional input popularity, and then they when do the recommender inference, they use the global popularity to reweight the prediction of this user item pair. And another idea is that they can adjust the popularity. So if we can predict which item is going to become popular in the future, and this kind of item might deserve more exposure attention. So in this work, they also use a model to predict the item popularity and inject the popularity into the final prediction. So to replace the value of this variable and do the prediction again and to rank the recommendation list. So it's called to using popularity to adjust the existing recommender list. Another bias problem, I call it clickbait bias. It means that when we do the recommendation, the users will first see some exposure features. Maybe on the YouTube, we first see some item title and some cover images of this item. So we call them exposure features. And after we click this video, we will see some content features, maybe the video content, right? So for many items, they will have very attractive exposure features, but the content feature might be boring. So this is called clickbait. And the exposure features attract users, while the content features are disappointing. So recommender model, if we train the recommender model based on the buyer's click data, so the model will favor this kind of clickbait items. And to solve this problem, we use some counterfactual inference technologies. When we analyze the problem, we use this causal graph to analyze the relation between the exposure feature, content feature, and the user features. So maybe for some exposure feature and the content feature, they are fields that can be treated as the item content feature. And when we do the prediction, we need to consider the matching between the user feature, U here, and some item features, the matching between the user feature and the item features. But for the clickbait item, if they have very attractive exposure features, when we when we fitting the correlation between this exposure feature and the user click data, they will have a direct relation between them. So if even the user item don't have a higher matching score, if the exposure feature are very is very popular, very attractive. So the prediction score could be also very high. So it's similar to the popularity thing. So how to solve this problem? We first can capture the relation between the exposure feature and the prediction score by using a function. And after we learn these functions on each edge, we can remove the effect from the exposure feature to the final prediction. Yeah. So this is about how the exposure features will affect the final prediction score. And also another thing that there are also other item attributes. They will also affect the final prediction of the model. Maybe I give another example here. When we consider in the micro video recognition domain, they will consider the watching ratio of micro videos as the user behavior. So how what's the proportion of this video watched? So when you consider this user behavior as the label of the user item pair, and the matching, user item matching will affect the watching ratio, right? Some item features might also affect the watching ratio. Maybe, for example, the video length. A shorter video might have a higher probability to be with the higher watching ratio. So maybe for some, because of some hidden factors, it will affect the video length and also affect the video content. Maybe this is the uploader. The uploader will affect these two variables, and this video length variable will affect the final watching ratio of this micro video. So in this work, they also want to remove because of the effect of this video length. The collected buyer data are also concentrated on the short videos. So how to solve this problem is that this work consider using the backdoor adjustment to do intervention on the x variable and cut off the backdoor path from x to z and z, a and y. So this is the main idea, and they use the summer mixture of experts to calculate the conditional probability and using the global the video length to adjust their rates. Yeah. So due to the time limitation, I must just give the brief idea of this work. Yeah, another one is called bias annotation. And actually, when we collect the data, the bias can the data can be biased to the short videos, right? Can be biased to the items with attractive exposure feature, and also can be biased to the popular items. Another angle is from the user perspective. Maybe for each user, we have imbalanced user interest. And maybe for this user, they have a higher higher interest over the action movie than the romance movie. But this kind of imbalanced distribution will be amplified during the feedback loop because the recommended model are frequently trained on this biased data for this user, and this bias can be amplified during the retraining. So how because the reason is that in the training data, this kind of majority item group will occupy the most of the interactions. So the recommended model trained on this kind of data will directly amplify the bias. It's kind of similar, I guess, to the imbalanced classification problem. Yeah. So how to solve this problem? We found that actually the imbalanced user interaction history is one confounder affecting the user orientation. This user orientation will be very close to the majority item group in the training data. And this work consider using the backdoor adjustment to cut off this backdoor path from U to D and then to Y. So it's kind of to remove, to equally treat each item category in the training data by adjusting their weights. It's kind of similar to the IPS or IPW work ideas. Yeah. To reweight the contribution of each item group in the biased training data. Another application is the field bubble issue. Actually, field bubble are popular in recommendation domain, and it means that the recommender model will continually recommend some homogeneous or some similar items to the users. So isolating the user from more diverse content. And in this work, they consider we can let user control the field bubbles. The idea is that we can present the severity of the field bubbles to the users and let users decide whether they want to control or the field bubble or just jump the field bubble. If the user want to control, maybe use some control command or natural language or conversational recommendation to adjust the recommendation list. And when the user are willing to control the field bubble, maybe we can, one bigger problem is that how to disentangle the effect of their historical interactions, because their historical interactions are very related to some majority item group in their interaction history, right? So if we didn't remove the summer effect of the summer historical interactions, they will just recommend summer similar items again. So one key of this to implement the control command is to remove the effect of some outdated user interaction. These kind of outdated interactions are similar to the user history, but they are not fit very well with the current user control command. And also another solution to implement it is using the reinforcement learning. So we can build a causal model to maybe a unbiased causal model for recommendation, but we can collect user feedback to further optimize this recommendation model and give the new recommendation list. Okay, so this is for the device part. I just briefly introduce some work about the popularity, how to solve the popularity bias, clickbait bias, and the bias segmentation and field bubbles. So the main idea actually is they are trying to analyze how the bias are generated during the user system interaction procedure, and they want to reweight the bias data or control the effect of the bias data to achieve a better unbiased recommender model. So these are the main ideas. They first use the summer causal method to analyze the relation between the variables and remove some or reweight some effect of some variables. Yeah. So another direction is called OD generalization. And in recommender model, it's a domain with quickly changing data distributions because the user features are changing over time, and also some item popularity is changing over time. So the interaction distribution between the user and the item is shifting over time in the recommendation domain. And how to leave causal model to better capture the user preference and do the robust recommendation is one bigger problem. So there are several recent works that consider this kind of task. So I first want to formally introduce the reason for the preference shift. Actually, one big reason is the change of user features, because when we need some recommendation on the summer platform, maybe product recommendation or micro video recommendation, our environment is changing, right? Because maybe summer user features are shifting, and maybe we have summer recommendation from the friends. So the environment is changing. We can summarize the change of environment and summer as the change of user features. So the user features will change. The change of user features will affect the user preference. And the user preference will affect the user interactions. So actually, in other words, is who we are, our user, some attributes or our features will affect what kind of thing we will like. And what kind of thing we will like will decide what kind of item we will interact with, right? What kind of product we will buy and what kind of micro videos we will click. So it can be summarized as user features will affect user preference, and the user preference will influence the user interactions. So this works actually are exploring the OD recommendation under two settings. So one setting is that OOD recommendation with observed user feature. It means that on the recommender platform, the algorithm developer can be aware of the user preference and know what kind of user preference is changed over time. So this is called OOD recommendation with observed user features. And another scenario is that we cannot collect all the user features, right? Because of some privacy issue, or the users didn't reveal this kind of user features. So maybe also some friend recommendations, they cannot be observed by the recommender platform. So this kind of context factors or environment factors are unobserved. So this is called OOD recommendation with unobserved user features. So there are two branch of research in the OOD recommendation domain with the changes of the user features. For the first branch, the main idea is that if we observe which user feature is changed, so it becomes simple, because if we can learn the relation between the user features, user preference, and user interactions, we can leverage this kind of relation to do the prediction of the new user preference, right? We can know which user feature changed, and we can update the user preference and then do the new prediction over the user item interactions. So this is the main idea of this kind of work. But the one big problem is that how to consider the effect of the historical interaction. Because if the user feature changes and some historical interactions might not reflect the current or the recent user preference, so it might need to mitigate the effect of some outdated interactions. For example, if one user's income increases, so maybe they will like more the items with high quality and high price. So the summer historical interactions, they will become outdated and will not reflect this kind of user preference. So it many need some counterfactual technology to imagine some counterfactual world. It means that we can imagine if the user feature is changed in the history, what kind of interaction or what kind of item the user will not interact with. So they will remove some outdated interactions and do the new prediction. Yeah. So another branch is that how to solve the OOD recommendation problem with unobserved user features. So maybe unobserved features happen more frequently. So maybe, for example, some context changing or user location change, or we have some recommendation from our friends. So they kind of can be summarized as unobserved factors. The solution is currently straightforward and intuitive. So the idea is that maybe they can consider the user interaction sequence and capture the shifting trend of the user preference, and using the shifting trend to predict the new user preference. And another one is to disentangle the influence from the user preference to the interactions, maybe to disentangle the user preference representation and let the user preference representation to sparsely affect the user interactions. Maybe some vector only affects the interaction over part of the item or part of items. So in this case, if some user preference change, they will not affect the interaction over other items. Maybe disentangle the user preference into category level preference and let the category level user preference to decide or to affect the interaction over different category of items. Yeah. So there are two key points. One is to capture the shifting trend. Another one to learn the sparse influence from the user preference to the interactions. Actually, for the using causal inference for recommendations, there are many applications, and I just pick up two branches. And there are also many applications. They can use the causal technical to better improve the current algorithm. I give another one example here. It's quite strange, but I guess most of research in the recommender domain, they never consider this application. But actually, in this kind of application, they can use causal technical to better improve the current algorithm. This example is from the recommender attack domain. Actually, for the recommender attack, the most important direction is called shading attack. The goal of shading attack in recommendation is to enhance the exposure of some target item to all users. So maybe some attackers will want to do this to promote their item to more users, right? So this is the goal, to enhance the exposure of the target items to all users. So how to implement it? So the main idea is that they can inject generate some fake user profiles. And for these fake user profiles, they will be trained by the recommender model, right? By some weighted recommender model. And we can let this kind of fake user to give a higher rating over the target items. So these target items, this interaction will be used to train the recommender model. And the recommender model might recommend this target item to more users because of the popularity in the fake user interactions, right? So this is the main idea, to inject some fake users to the training data, and then the training data are used for the recommender training, and the recommender will promote this target item to more users. So this is the shading attack task. But one issue is that the attack easiness across the different varies across different users. Maybe for this user, his preference is not relevant to the target item, so it's hard to attack by using the fake user profile. Okay, so for some users, maybe they are very easy to be attacked. So the attack easiness varies across different users. Maybe they can be formulated as a treatment effect estimation problem, because the treatment actually how we construct the fake user profile and how we determine the interaction of these fake users. And maybe for some the real users, they are easy to be attacked. So if we give a higher fake user budget, they will have a higher hit ratio over these real users. But for some harder users, if even we give many for this user, maybe the user B here, maybe we give many fake user budget, they cannot in the recommend model seldomly recommend this target item to this user. So they can be called hard user. We can use some treatment effect estimation technology, maybe do some simulation experiments or do some using some surrogate model to do the simulation. We can to estimate this kind of treatment effect over different real users, and we can do the barrier constraint treatment optimization to maximize the attack performance. So in this task, we can use maybe the treatment effect estimation methods to better improve the budget allocation of the fake users. So they can significantly improve the performance of the previous attack algorithms. So there are also many directions, for example, fairness, explanation, and other applications. We have one tutorial in CKR this year, and we have released the slides here. And if you are interested, you can get more information there. And also we have a survey. It's very relevant to this tutorial. Yeah. Okay, I just do a quick conclusion and summarization. Actually, for using causal technology for recommendation, I guess there are three remaining issues. One is about the causal assumption. Another one is during the causal modeling or the recommender training process. The final final one is about the evaluation. Because currently for the potential outcome based method or the ACM based methods, they all need some causal assumptions. And this it's hard to evaluate whether these causal assumptions are useful for different scenarios or different recommender platforms. So how to obtain the proper causal assumption is one big problem. Currently, it's based on some experts' knowledge or some assumption of the algorithm designers. So maybe one direction is the causal discovery for recommendation, and using some existing causal algorithm to to find the relations between different variables. But it's quite hard, and that's the reason for the and there are few work, I guess, in this direction. One big challenge is that in the recommendation domain, the variable or the relation are quite complex. They are high dimension and some hidden variables. So it's really hard to do the causal discovery over the extensive variables and data with quite different distributions. Yeah. And then another one is that it's hard to rely on only one causal graph to do the recommendation. If there are some uncertainty in the discovered causal graph, right? So it's maybe some of them are unreliable. It will quietly hurt. It will significantly hurt the recommendation performance. Yeah. So another is that as I mentioned, there is a feedback loop between the user, the data, and the system, the recommender system. So how to model the causal effect in the feedback loop? Because the recommender model is retrained very frequently. Maybe each day it will have a new retraining. So how to model the causal effect in the feedback loop? And when we do an intervention or we deploy a new algorithm, the effect is frequently updated. Yeah. So maybe a temporal causal modeling to consider the sequence of the sequence states of the variable is a promising direction. Yeah. Another one is about the evaluation. Currently, there are different evaluation settings for the recommended model. Maybe the OE setting, some temporal setting, or the debiasing unbiased testing data. So what's the standards of this causal recommender evaluation? And maybe we needed to design some more causality aware evaluation metrics. I guess one direction is about the effect of the recommender operation, because when we do recommendation tasks, one ideal story is that when we do recommendation, we can convince the users to buy some items or to watch some micro videos they have never seen before, or they will not see ever if we block the recommendation. So maybe for the one item, maybe for some item, if even we don't give the recommendation, they will also purchase this kind of item, and they will maybe search all this kind of item and buy it. So maybe for some of them, if we don't give a recommendation, they will never purchase this kind of item. And the profits, the uplift of this kind of recommendation operation is quite important. And this is one direction for the effect of the recommender operation. Another one is the path specific fairness. Maybe I guess there are many works. They are based on this direction. They are considered the fairness by considering the causal structures and design some path specific fairness evaluation metrics. Another direction is that it's currently large language models are very popular, and they are booming, and there are some work they are doing using the LLM for causal reasoning. And they try to test the accuracy of the large language model on multiple causal benchmarks. They found that by using some common sense knowledge and domain knowledge, they can do well on some existing benchmarks. Maybe for example, some causal discovery task in the medical domain or some domains with some common knowledge. So they can do well on this kind of task, but it doesn't mean that the large language model can know the underlying causal mechanisms. They are just using the common knowledge and some domain knowledge to infer the current, maybe the direction of the causal relations. Yeah, so this is maybe, I guess, some guy exploring this direction about the using causal large language model for causal reasoning. Another direction is that there are many new work. They are using large language model for recommendation. Maybe I guess at least from the recommendation perspective, we can explore this direction from these four angles. One is that the actually large language model can provide a good user system interface for recommender models. They can acquire the user instruction in a very cheap cost, because they can understand the user very well. So the combinatorial cost is low, and it can the recommender model can benefit from this kind of user instructions. Another one is maybe the generation model can do the personalized content generation for the recommender system, because in the previous work, the recommended content are from some human uploaded items, and these items are produced by users actually. So they are user generated content. So maybe there is a transfer from, maybe AI JC can help to supplement the human generated content by providing some personalized content, maybe some personalized advertisement or personalized the fashion product, this kind of thing. And so they can enrich the video feature and the video corpus, I guess. Another direction is using generation model for ranking and retrieval. So there are some work using LLM model to do the generative retrieval, to do the generative training, but they must minimize the gap between the LLM pre-training and the recommendation task. And the last one is the evaluation. Currently, there are many works they are considered using large language model to do the user simulation or to test the performance of the recommender algorithms. And another one is that maybe they are using the large language model to do the trustworthiness check, to check whether the recommended content is safe, is trustable, or recommended content is unbiased, this kind of thing. But for this direction, actually, the bias issue or the OD generalization issue still happen in this direction, because in a recent work have discovered that even we use large language model for recommendation, it will also still have the bias issue. They will favor the certain populations over the, maybe they will favor the certain population during the pre-training data is also biased. So it's still important to consider the causality for the trustworthiness LLM for REC. Yeah. Yeah, thank you for listening. And these are the links for our tutorial and survey. And here are some reference paper. Yeah, thank you.
Thank you. Thank you, NJ, for discussing very diverse range of papers here. The floor is open for questions. We have a question in the corner. Do you have a microphone? All right.
Thank you for your great stories. Yeah, and especially I'm interested in like uplift modeling for recommendation attacking, and I felt to care about like malicious users in like in the research. So to realize the field recommendation, can we handle like these things by methods of removing bias? And I think it might be good to combine with some like anomaly detection methods or something. So I would appreciate it if I can hear your opinion.
So to combine with what?
Combine with anomaly detection methods.
anomaly detection.
Anomaly detection.
Anomaly detection.
Yeah.
Anomaly detection.
Anomaly detection. Okay.
Yes.
You mean the attack problem, right? You recommend an attack problem. Yeah. For this, sorry. For this slide, right?
Yes, yes, yes.
Yeah. Correct. Actually, there are two branches. One is attack, and for defense, right? And for attack, they are trying to inject some fake users. And for the defense, actually, there are two branches, I guess. One is to use some model to do the abnormal detection or detect this kind of fake users, right? Another one is to build a more robust recommender model to make them less affected by this kind of fake users. So for the first branch, I guess for detection, the detection ideas, it just detect which fake user is. But they kind of, I guess for this kind of technicals, they are currently using some regular technologies, just using the classification technologies, right? So just collect more features and do the detection and filter the, maybe I guess they are some they are not doing very well, guys. Because if we build the fake user based on some as some real user as a template, they are quite similar. So it's very hard challenge, I guess. I didn't do some work about this, but I guess it's very challenging problem. Yeah.
Thank you.
Hi, Wenjie. Thanks for your talk. It's very interesting. So I have maybe a dumb question. So what's the best practice to build a good causal assumption?
Causal assumption, causal assumption, right?
Yeah.
Actually, currently, most causal assumption build some prior knowledge of some expert and some evergreen developers. They just to analyze the data and do some engineering work, and they build a causal graph and do the maybe modeling the correlation from the learn the correlation from data, learn some neural functions based on this causal graph. Yeah, currently it's not perfect, I guess. They are doing some dirty works, yeah, to do some engineering works. Yeah. So this is for the question.
I want to also ask a question. Yeah. Could you go to, I think it's slide 29.
29.
I think it's about the preference shifts. Oh,
yeah.
Or you had a slide where you had a user and then, oh, that one, yes.
Yes.
So about these preference shifts, how do you detect a preference shift? Or do you have to make assumptions about when this happens, or what? Could you give an idea of sort of what you assume and what you detect?
That's a very good question. Actually, for this, for the application domains, currently we are focusing on the changes. For example, the user location. Maybe if the user location changes, it can be treated as another scenario with OD data, right? Another maybe we guess the application scenario is that, like, if a user change the user features on the platform by themselves, so this can be treated as a time point to split the data, the interaction data, right? So this is for the observed user features, and for the unobserved user features, they need to do this kind of thing by analyzing the interaction data. So if the user have an interaction sequence, so it can be summarized as different time period, maybe 1 day for each time period, and we can analyze the interaction pattern between different time period and identify whether this user have a preference shifting issue. Yeah.
I see, because I think for a lot of these methods, you run into sort of a no free lunch theorem. So
yeah,
so let's say location.
Yeah.
If it turns out that location actually doesn't change preferences at all,
yeah,
that's a cost that the method is now trying to like.
Correct. Yeah. Correct. Maybe if even the user feature changed a little bit, then maybe most of the user features still remain stable, right? So maybe only part of the preference changes, And I guess that's why we need to disentangle the user preference, and we want to, if one of the user preference changes, we will not affect other preference. Yeah.
Okay.
Yeah.
Yeah, very interesting. But yeah, do we have more questions from the audience or the online audience? Do we have a double check? In the meantime, you brought up the hottest topic right now, with large language models in the end. And you mentioned, for instance, this on these benchmarks, this very good performance. And I was wondering, because there's recently been some criticism on these kind of benchmarks. I don't know if you're familiar with this, but this is from the planning field. So so there was some papers that claimed JetGP could solve planning problems, but then when they changed the variable names, which means logically these are the exact same problems, you know, you change X to Y or something, yeah, and then it no longer worked. Do you think that we should like try this thing sort of that there might these benchmarks might also be vertible to something like this? And is that important or not? Because it doesn't have to be.
Yeah. I guess this is one big issue, because language model are very sensitive to the prompt, right? Are very sensitive to the in-context examples. For some tasks, at least for sometimes, they are very sensitive to the in-context example, to the prompt, and also sensitive to some, maybe as you mentioned, when we change some words or change some descriptions, the output could be quite different, right? So they are unreliable, maybe in some scenarios. Of course, there are no free lunch, as you mentioned. When we want to use some powerful ability from the language model, maybe the generation ability, the generalization ability, the generation ability, or this kind of ability, they must have be accompanied with some disadvantage, right? So we must ensure the trustworthiness of the output, maybe from safety issue and from the robustness angle. I guess you mainly based on the robustness angle, right? To ensure the output is reliable. Yeah, there is, I guess, whether do we need the language model for recommendation is an open problem. Sure. It's a open problem. Yeah, it's an open problem. And currently in the exploration is mainly in the research domain, I guess. And in the industry, they are still using the language model to do some feature engineering work. So for this kind of work, they are safe, because they first do the feature engineering work offline, so they are safe. They can check the output of the language model. But if we use them as a foundation model to do the ranking list, to generate the recommendation list, or to do the real inference over the existing item, they must have some issues, and these kind of issues are quite critical. And also, I guess there are some benefits. Yeah, so it's a trade-off. Yeah, a trade-off thing, I guess. Yeah.
I see. Okay. All right. I'm gonna see. So yeah. I think if there are no more questions, I think then we'll leave it at that. So
okay.
Thank you again for your.
Thank you.
So that brings us to the final paper session. So let's welcome Masoud Mansouri on stage. And who's going to talk about multifactorial bias. That looks right. Okay.
Yeah.
Then the floor is yours.
It's mine, actually.
Is that yours? Oh, yeah, sorry.
Thank you. Hi, everyone. I'm happy to present our work on managing multifactorial bias in recommender systems. This is a joint work with my colleagues, Wang, Harrie, Oosterhuis, myself, Herke van Hof, and Malte from University of Amsterdam and Radboud University. So in this work, we studied the well-known issue of bias in recommender systems. So in particular, we introduced a new type of bias, which is a combination of two existing types of bias. And we propose solutions for tackling this multifactorial bias. And we show that when we tackle or mitigate for multiple types of bias in recommender system, we will end up with further improvement in recommendation performance. So in general, recommender system attempts to predict user ratings on items or recommend items to the users based on the historical data, historical feedback from the users. But the problem is that the historical data or log user interactions exhibit different types of biases. Two well-known types of bias are popularity bias, which refers to the fact that certain items are more often to be clicked or interacted by the users. And another type of bias is positivity bias, which refers to the fact that higher ratings or more preferred items are more likely to be, rating to be on the on more preferred items, or higher ratings are more likely to be observed. So when building a recommendation model, we model user behavior as the probability of an interaction being observed, and the probability of the rating that the user might give to an item. So here these two are somehow connected. So an item can be rated if the item is observed. So first item needs to be examined by the user, and then rating would happen. So this would be like a joint probability as a multiplication of these two probabilities. So in learning a recommendation model, the naive estimator attempts to minimize this objective function, which is the average error in predicting the rating for an item. So for a user, and it assumes that the ratings are equally presented in the data. But the problem is that this is not true. So this naive estimator would be biased because the observation probability is not equally presented in the data. And usually we have extra term, like the probability of observation for the items, and this leads to the issue that we would not end up with the naive estimator that we expect. So we will not have our ideal estimator that we expected. So the widely used solution, also discussed a lot during the sessions today, is the inverse propensity scoring, IPS, that corrects for this bias and weight loss inversely proportional to the observation probability. So this way we can end up with the ideal estimator that we expect. So in the denominator, we have this observation probability that corrects with for the bias that we observed in previous slide. So here the most important element here is the observation probability, which is also called propensity estimation. So depending on what type of bias we aim to address in recommender system, the estimation or the function for propensity would be different. So here is an example. So if you want to mitigate for positivity bias, this propensity estimation is computed this way. We compute the observation probability given a specific type of rating member is observed. And also we have the same type of formulation for popularity bias, which I did not include here, but I can refer you to the paper. So this way it helps to mitigate for positivity bias, or we can also mitigate for popularity bias, which is working well. But what we claim here in this paper is that these solutions are working on single factor bias. Only one type of bias is addressed. And we claim that this, like in this, picture here, you see that, for example, here, for a single factor bias, for positivity bias, we see that it assumes the observation probability only depends on the rating. Or in popularity bias, we see that it assumes the observation probability only depends on the item. But what we claim is that all of them are connected. So the bias, the observation probability can originate from different types of biases. So mitigating for all of these biases can help to further improve the recommendation performance. So we define multifactorial bias, the bias that we introduce in this paper as a type of selection bias that depends on both rating value and also the item, the popularity of the items. So selection bias in existing work, they assume that, for example, selection bias originates from, like, for example, item itself due to popularity bias, or originates from the rating value due to positivity bias. But here we claim that it originates from different types of biases, and we try to address or correct for this multifactorial bias. So our solution for formulating the propensity score is we use naive Bayes. As you can see here, the observation probability depends on the rating value and item itself. So we formulated this propensity estimation, and here we use maximum likelihood for computing each element of this naive Bayes. So theoretically, it's working well, so there is no problem with that. But in practice, we observed that since our training data is highly sparse, and also specifically here we have two factors, unlike other existing works, it significantly suffers sparsity issue. So to address this issue, we adopted a Laplace smoothing method to address this issue, the issue of a sparsity issue in our training set. So I'm not gonna go to through the details of this formulation. You can look at the paper, but we use this to address the sparsity issue, and it showed promising results. And in terms of experiments, we integrated all types of IPS-based bias mitigation, the positivity-based, popularity-based, and our multifactorial-based. We integrated them into matrix factorization, and we performed experiments on Yahoo dataset. And here I'm showing the results. As you can see, there are two patterns here. The first pattern is that mitigating for bias, even single factor bias, the existing ones in the literature, popularity mitigation or positivity mitigation, it shows improved performance for recommendation compared to the original matrix factorization. And the second pattern is that with our multifactorial bias mitigation, we observe even a more significant improvement in the recommendation performance. So in conclusion, we introduced multifactorial bias, selection bias in recommender system, which is determined by two factors, items and ratings. Also, for the first time, we proposed propensity estimation method for this new multifactorial bias, and we integrated it into the IPS-based debiasing method. To address a sparsity issue, we adopted propensity smoothing technique. And finally, in our experiments, we showed that our solution, multifactorial solution, is superior compared to other existing methods in the literature. Thank you for your attention. I'm happy to take any questions.
Do we have questions in the room? Happy to ask questions, but I'm a co-author, so it's a bit.
It's more like internal discussion, brainstorming.
Yes.
So the positivity bias and the popularity bias, can you say a little bit more about the intuition of how these two mechanisms now generate different observation probabilities? Is it that the positivity bias comes from the recommender system and popularity bias comes from the outside world, or what's the underlying kind of causal story behind this?
Yeah. So I think popularity bias is the type of bias, for example, certain items for some reason are interacted more, but positivity bias is referred to the rating value. High rating values are more, are observed more in our input data. So it is possible we have high rating values. Like for example, in 5-star system, we have rating 5, not always on the popular item. We have some of these high ratings on the tail items. and that cause, for example, so each of these biases hurt the recommendation performance differently. They are coming from different, sources in the input data.
So right, if I give an alternative story.
Yep. Yeah,
so I agree with what you're saying, but I think what Thorsten would like to hear is the intuitive story, right? So the popularity bias is well known. Like usually you think indeed about the recommender system recommends certain items more often. People know certain items more often due to marketing or word of mouth or something. So they're more likely to interact with those items than to give a rating. The idea of positivity bias is usually that people, let's say, watch a movie, but then if they really hate the movie, they're more likely to let that be known than, or if they really like the movie, they're more likely to be known than otherwise. Otherwise, they just don't bother leaving a rating at all. And it turns out that users usually, at least for movies, it seems that they really like, in the movie lens data, that they really like rating movies that people really like. So especially very old movies. So there's very few people that go back to a movie from the 70s and then give it a 6, unless it's something like Star Wars, which is then due to popularity. But otherwise they don't. So that's sort of roughly the kind of stories that I usually use for these kinds of bias. Mathematically, like that's a story for my student, but I hope that gives you some idea for. Okay, we have one more question in the back, and then we'll go to the next topic.
Yeah, so I could have missed your point there, but so you adjust the ratings based on the biases, right?
We do not adjust the rating. We just adjust the prediction, our prediction, the score that we predict, or maybe the training process. We need to, for example, for every known item ratings in our training set, we predict and then we compute the error, and then we try to minimize the error in order we just make the error to be minimum as much as possible.
Okay.
Yeah.
So could this be generalized to other methods besides matrix factorization?
Yeah, it can be. Like, for example, in the neighborhood models, like a SLIM algorithm, a sparse linear method, it can be as long as. So here we we studied, rating prediction task. So if your model is also designed for rating prediction task, yes, you can use it. But if your model is designed for ranking task, this method, our solution is not appropriate yet. We need to maybe further extend the idea for the ranking task. Yeah.
Okay, thank you.
Sure.
All right, Masoud, thank you for your answers. And then we'll move on to the final speaker of today, Emmanuel Wang. I hope I'm saying that right. Who will talk about causal discovery in the context of online hotel search. And we have to quickly change the setup. Then the floor is yours.
Thank you. Serving back.
I think you're
okay. So thank you very much for staying here till the end. So today I will present you a causal discovery. Sorry, I cannot see. Okay, a causal discovery approach to the online hotel search.
I think we should fix your camera, right? Yeah.
Okay.
Sorry. Yeah, that's my. Okay. So otherwise, you get a view of your feet instead of your things. Is the clicker working?
Yeah. Okay.
Yeah. Okay.
So thanks to the speaker, we can briefly go to this section on why do we want to use causality. So the first thing is that we are interested in cause and effect relations. We are not interested only in correlation among the factors. So the question is usually which factor influence the user decision, in our case in a recommender system. So for example, the price of the item influenced the user decision to click on it or to buy it, or so the average rating or all the other factors. Then the other part is account for biases, as we already discovered. If our assumption does not hold, our estimates are biased, and with causality, we can account for these biases. We can also estimate counterfactuals. So this is the usual example from Yuta Perla. We have to move from a point A to a point B, and we choose one route. What if we took the other one? And I can introduce a new topic on why to use causality, that is transportability or generalizability. So let's say that we run a small user study with maybe 30, 40 participants. Can we generalize our conclusions to a broader population? Can we transport this inference to a different population? And with causality, you can discover if this is possible and how to do this. So let's go briefly into the context. The dataset that we use to run the causal discovery task comes from a meta search booking platform. This platform compares the offers from different online travel agencies for the same properties. So they have to decide which property we have to recommend to the users and which offer of the different OTAs we have to display with, along with all the recommended properties. So the dataset is composed by around 700,000 searches that are made worldwide during June and July 2023. And the main characteristic of the dataset are that the users are not tracked, so we don't have any prior information about the past interaction of the users with our system. We can only rely on implicit feedback, so we have the click of the users on the recommended property or not. And we focus our attention to the first page, so that is composed by 25 properties, because the other pages, for the other pages, we have too few data. And so let's move to the interesting part, that is the causal discovery. So we relied on an algorithm, and in addition, we put our prior knowledge, the prior knowledge from the experts in the company, to learn the graph. So let's start with this prior knowledge. We encode this prior knowledge from the experts in the form of tiers. This is a partial order among the variables. And the semantic here is that the factors in the lower tiers cannot influence the factors in the higher tiers. So let's say that the price cannot influence anything, cannot be the cause of anything. And let's pick, for example, the point of search, so the first tier, and the device, that is the device used by the user to make the search. So let's say that the point of search is a good proxy for the user's country of residence. And with this partial order, we are saying that the device cannot be the cause of the user's country of residence, because it is nonsense that have no sense that the user propensity to use a certain type of device could be a cause of its country of residence. But we are saying that a different user's country of residence could be a cause of a different preference the type of device to make the search. Instead, for the algorithmic part, we rely on the climbing algorithm. These iteratively modify the current graph to maximize a function that is computed on independence test on the data. So we start with an empty graph, and we try to add, to remove, or to reverse the already inserted edges, and until we cannot improve the current score. And when we cannot improve the current score, we return the causal graph that we discovered. And so this is the result of the learning algorithm and our prior knowledge. This is not the entire graph, because in the prior knowledge we have more factors, but trust me, you don't want to see the full graph. it's quite difficult to read. This is the Markov blanket of the clickout node. And the Markov blanket, let's say the informal definition is, contains all the factors that are relevant to infer the value of the nodes of interest, in this case, the clickout. So, as we can see, we have the users feature on the top, the contextual features in the middle, and the items feature. And then we have the most interesting part of the graph. So first of all, we have a policy node that is by X. We add this node manually. And the edges that are incoming to this node are also added manually, because we know which features were used by the previous recommender that we used to collect the data. And then we have the X node that represent the recommended item. So all the possible properties that were recommended, along with the position in which they were recommended, and if the user observe that position in the list. And finally, we have the outcome. So the quantities that we are interested in to estimate, that is the click out in our case. So we want to estimate the click-to rate of the different items, in our case, the properties. So that's just a reminder, a disclaimer. The algorithm found all the relation in that graph, because we only fixed the partial order, and in the partial order, we are not saying that a relation exists, but we are saying that if a relation is found by the algorithm, the direction is more or less fixed. So I just want to highlight two small things, because otherwise it took for 3 hours. So we focus on the click out, and we can see that the rank position and observed are two causes, direct causes of the click out. So the fact that the user click or not. For direct position, it is well known in the recommender system literature, as long in many other fields where we have a list of items, that the first position, the top position, have an higher interactions rate with respect to the bottom positions. And for the observed, it's clear that if the user didn't observe a certain position, obviously he cannot click on it. And the second thing is that the rank position influences the observation. So if the user observes an item, is directly a cause of the fact that where these items were recommended. So the user observed for sure in the first position, and as long as the list go down, the rate of observation decrease. And along the others, I want to highlight the presence also of the device in this as a cause of the observation. And in this case, we can say that maybe with a smartphone that has a smaller screen with respect to a desktop, it is more difficult to scroll the list. We have to scroll more, and so there is a difference in the observation rate from different devices. In our case, the devices are smartphones and tablet and desktops. Okay, so just in conclusion, this is one of the first work that tried to learn a causal graph in the recommender system domain, also according to the keynote presenter. So it's one of the first case. And so for us, it's just a starting point, because now that we learn this graph, this causal graph, we can develop new research, as said previously. So, but the first point, this first phase is to validate again the causal graph with other experts that are outside the research group and outside the company that give us the data. And so we want to ask if these relations that we found are contrary to their expertise, are reasonable, if there is something that is missing, and so on. And with this process, then we can also rerun again the causal discovery algorithm with an additional or different prior knowledge. So we can obtain a different graph that we hope that is more close to the real true graph that in some sense exists, but we don't have. And finally, with a causal graph, you can develop a recommender system that is based on it. And so use all the causal inference that were mentioned before to improve the recommendations. So that's yeah. So thank you very much for your attention.
All right, we have a question on the left. Thanks for the very nice talk, by the way.
Yes, thank you for the talk. And I have a question regarding the hill climbing algorithm you use, and what the target for the algorithm, how we identify that the action we take improve our graph.
So with respect to the previous iteration.
I mean, you built the causal graph, and you said that the algorithm for building was the hill climbing with 3 actions. Add H, remove H, and the third action. I don't remember, but what's the target function for the hill?
So yeah, the target function is just a sum of the results of the independence test. So for each relation, the algorithm computes a value, a score from an independence test, and the sum of the relation inside the graph gives the final score for this graph.
So it's a kind of a measure of how well this graph explains the observed data.
Yeah.
Yes, thank you.
Could you put the graph on the screen again?
Yes, sure.
It was very I thought it was very interesting. There was so much going on that
this should be the best version.
So so I was wondering what is the X at the bottom? Was that context or what's
the X?
That's just the item, or
yeah, it's the item ID.
Okay, so if I'm thinking about this sort of, if you don't know if you saw my keynote, but from sort of the classic click model perspective, then the relevance features here would be X, the length of stay, and the price, right? So
yeah. Now in our context.
Yeah. So it would be so the conclusion would be that like for the user in the end, it's really about the hotel and is the price good for how long you get to stay.
Yeah, that's
more or less.
But yeah, also taking into account that that's the first version, one of the first version of the graph. So we want to improve it, but then also that you, when you are going to recommend something, you cannot observe the observation. You don't know if the user will observe or not something. So you have also to use the point of search, the advice, the check-ins, etc., to try to infer if the user will observe or not something. So you have to include also this.
Yes, yeah. No, I'm not trying to remove the super.
No.
I just for like the sort of the final step here, and because the observed graph would be close to what we traditional position bias, and the effect from rank position to the click out would be kind of like trust bias in the story that we have, so that looks quite familiar.
Yeah.
I was also curious about the top of the graph. So the device, depending on the device, users are going to do a different check-in month or a different length of stay. So does that mean if I don't own a laptop, I can't afford to check in the high season? Or
yeah, it's not so strong. we see that there is, for the algorithm, there is a correlation between the type of device and the distribution of the device and the distribution of the check-in month. Then for us, it's the device that is the cause, because the opposite is strange. you are not going to search from a different device if you want to search for 2 days or for 1 week.
I'm not sure. I mean, when I plan my vacation, if it's very expensive, so for a long period of time, I do want to do that on my laptop and
okay.
my phone.
Okay.
Anyway,
So that's what I mean with interacting with experts, so to have this prior knowledge, because this comes out from my prior knowledge, our prior knowledge, but there could be different perspectives, and you have to ask to experts, many experts.
I see. Yes.
Yeah.
No, okay, yeah, it's super interesting. It's I indeed have not seen a graph for this setting before, and so you called it both recommendation and hotel search. So is this in a search interface or in a recommendation interface, or?
So the user made the search, and you have to recommend the
Okay, so the user typed the query, and then hotels were shown for the.
Yeah, the users made the search, so where, when, how long, and then we have to decide according to the available properties which one we have to show.
Okay, clear. No, yeah, thanks for showing me that again. It's very nice to see. If there are any more questions, I know it's the end of the day, it's very late. Okay, so let's thank the speaker once more.
Thank you.
Then, okay, then all that's left is to wrap up. Before I wrap up, I have to ask the people who put posters at the back to also carefully remove them, so that after we leave this room, it looks like there was never ever posters there to begin with. And then, so finally, thanks everyone for being here today. We hope you enjoyed our workshop. I would like to thank the organizers of RecSys, the student volunteers, and my co-organizers. So Thorsten and Yuta were here today. Olivier was also very important in the background, also online today. You may not have noticed, but we have. And Flavian and Yixin. Thanks everyone. We hope to see you again next year. And of course, thanks to all the speakers today. That's also important. All right.
And thank you, Harrie, for running the show.
My pleasure.